Patterns of Power: Mastering the Gang of 4 Design Principles for Elegant Software. Chapter 1: The Art of Software Design. Why Patterns Matter. Imagine for a moment that you are not building software, but a magnificent structure. A soaring skyscraper, a grand bridge, or even just a sturdy, comfortable home. When architects design these marvels, they don't start from scratch with every single beam, every support. They rely on established principles, tried-and-true solutions for common problems. They know how to build a strong foundation, how to construct an efficient truss system, or how to design an arch that bears immense weight. These are not rigid templates to be copied blindly, but rather proven ideas, collected over centuries of building, that inform their creative process. Software development, at its heart, is very much the same. It's an act of construction, a blend of engineering and artistry. While the output isn't tangible bricks and mortar, we are still building complex systems that must be robust, flexible, maintainable, and understandable. We strive to create digital structures that can stand the test of time, accommodate change, and serve their users effectively. Yet, all too often, software projects can feel less like elegant architecture and more like a never-ending tangle of wires and pipes. We've all seen it, or perhaps even contributed to it. Code that's hard to change, bugs that seem to pop up everywhere, and new features that break seemingly unrelated parts of the system. This often happens because, in the rush to deliver, we focus on what the software does, without enough thought to how it's built or how it's organized. This is where the art and discipline of software design come in. Software design is about more than just writing lines of code that make a computer perform a task. It's about structuring your program so that it is clear, extensible, and adaptable. It's about making conscious decisions about how different parts of your system will interact and how they will respond to change. Good design anticipates needs, manages complexity, and creates a logical flow. Bad design, on the other hand, can lead to what's often called technical debt, a metaphorical mortgage on your time and resources, where every small change costs more and more because the underlying structure is unsound. As software systems grow and evolve, developers frequently encounter similar design challenges. How do you ensure that only one instance of a particular resource manager exists? How do you allow new types of operations to be easily added to objects without modifying their core structure? How can different parts of your application communicate without becoming tangled together? These are common, recurring problems, and highly skilled software designers have, over time, developed elegant, reusable solutions for them. These reusable solutions are what we call design patterns. The concept of patterns didn't originate in software. It was first popularized in the field of architecture by Christopher Alexander and his colleagues, who documented common solutions to recurring building and urban planning problems in their seminal work, A Pattern Language. They observed that certain spatial arrangements and design solutions appeared again and again because they effectively addressed human needs and aesthetic concerns. Inspired by this idea, 4 brilliant computer scientists, Erich Gamma, Richard Helm, Ralph Johnson, and John Velasides, often collectively referred to as the Gang of 4 or GOF, applied a similar approach to object-oriented software design. In their groundbreaking 1994 book, Design Patterns: Elements of Reusable Object-Oriented Software, they systematically documented 23 recurring design solutions that they had observed in well-designed software systems. They didn't invent these patterns. Rather, they discovered and cataloged them, giving them names, explaining the problems they solve, and detailing their structures. So, what exactly is a design pattern in the context of software? It's not a ready-made piece of code that you can simply copy and paste. Instead, it's a description of a problem and a generalized, abstract solution to that problem within a particular context. Think of it as a blueprint or a recipe for tackling a specific design challenge. It provides a common vocabulary, a shared understanding, and a proven approach. Why should you, as a software developer, invest your time in learning these patterns? The benefits are profound and numerous. A shared vocabulary. Imagine trying to discuss a complex architectural detail without common terms like arch, dome, or buttress. Similarly, in software, patterns provide a powerful, shared vocabulary. When you say, "Let's use a strategy pattern here," Other developers who understand patterns immediately grasp the core idea that you're aiming for interchangeable algorithms or behaviors. This streamlines communication and reduces ambiguity. Proven solutions: you don't have to reinvent the wheel for every common design problem. Design patterns encapsulate wisdom gleaned from years of collective experience. By using a pattern, you're adopting a solution that has been thoroughly tested, refined, and understood by countless developers across diverse projects. This reduces the risk of introducing subtle bugs or architectural flaws. Improved design understanding. Learning patterns is more than just memorizing solutions. It's about understanding the underlying design principles. Each pattern is a masterclass in how to apply concepts like encapsulation, polymorphism, and abstraction effectively. As you study patterns, you'll naturally develop a deeper intuition for good object-oriented design. Flexible and maintainable code. Patterns are often about managing dependencies and making systems more adaptable to change. They help decouple components, making it easier to modify one part of the system without affecting others. This leads to code that is more flexible, easier to maintain, and less prone to breaking under the pressure of new requirements. Accelerated development. When faced with a known problem, reaching for a proven pattern can save significant time and effort. Instead of spending hours grappling with a potentially complex design conundrum, you can apply a recognized solution, confident in its architectural soundness. Of course, patterns are tools, and like any tool, they must be used wisely. They are not a silver bullet to solve all problems, nor should they be forced into situations where simpler solutions would suffice. Over-engineering, applying patterns unnecessarily, can lead to overly complex code that is harder to understand and maintain. The goal is not to use as many patterns as possible, but to use the right pattern for the right problem at the right time. This book will guide you through the journey of understanding the 23 foundational gang of 4 design patterns. We will explore each pattern by first identifying the core problem it solves and building a compelling real-world motivation for its use. We will then examine its fundamental structure, understanding the roles its participants play and how they collaborate. Crucially, we will also discuss the consequences, the advantages and potential trade-offs of applying each pattern. We will illuminate these abstract concepts with relatable analogies, providing a clear mental model that transcends specific programming languages. Our journey will be structured into 3 main categories, reflecting the primary intent of each pattern. Creational patterns. These patterns deal with object creation mechanisms, trying to create objects in a manner suitable for the situation while increasing flexibility and reuse. Structural patterns. These patterns concern the composition of classes and objects. They explain how objects can be combined to form larger structures while maintaining flexibility and efficiency. Behavioral patterns. These patterns are about communication and interaction between objects. They identify common communication patterns between objects and realize these patterns. By the end of this book, you will not only have a firm grasp of these essential design patterns, but, more importantly, you will have developed a keen eye for good software design. You will be equipped to approach complex challenges with a richer vocabulary, a deeper understanding of architectural principles, and a toolbox of proven solutions to craft truly elegant and powerful software. Let our exploration begin. Chapter 2: Essential Object-Oriented Principles for Patterns. In our previous chapter, we established that design patterns are not just random tricks, but rather proven, reusable solutions to common problems in software design. They are the blueprints that help us build robust, flexible, and maintainable systems. But where do these blueprints come from? What are the underlying principles that make them effective? Just as an architect must understand the fundamentals of physics, materials science, and human behavior before designing a structure, a software designer must grasp the core principles of object-oriented programming, OOP. Design patterns are, in essence, highly sophisticated applications of these fundamental OOP principles. Without a solid understanding of these foundational ideas, patterns can seem like magic spells to be chanted rather than logical solutions to be understood and applied thoughtfully. This chapter will serve as our toolkit preparation. We'll explore the essential object-oriented principles that underpin virtually all the design patterns we will discuss. Think of these as the basic building blocks and guidelines that enable patterns to work their magic. Let's begin with the primary pillars of object-oriented programming. Encapsulation, the hidden power. Imagine a car. As a driver, you interact with the steering wheel, accelerator pedal, and brake pedal. You don't need to know the intricate details of how the engine combusts fuel or how the brake pads grip the rotors. All that complexity is hidden away, encapsulated within the car's mechanics. You only interface with the parts necessary for operation. In object-oriented programming, encapsulation is the principle of bundling the data attributes and the methods, behaviors that operate on that data into a single unit, typically a class. It then restricts direct access to some of the object's components, meaning you can interact with an object through a defined interface, its public methods, without needing to know or worry about its internal workings. Why it matters for patterns. Encapsulation promotes modularity. It allows changes to an object's internal implementation without affecting the code that uses that object, as long as the public interface remains consistent. This drastically reduces ripple effects, where a change in one part of the system unexpectedly breaks another. Many patterns, like the facade or adapter, rely heavily on encapsulation to simplify interactions or provide a consistent view of complex systems. Inheritance, building on what exists. Inheritance is a mechanism that allows a new class to be created from an existing class, inheriting its properties and behaviors. The new class, called the subclass or derived class, can then add new features or modify inherited ones. This establishes an is-a relationship. A sports car is a car. Why it matters for patterns. Inheritance is crucial for achieving polymorphism, which we'll discuss next, and for building hierarchies of related objects. Some patterns leverage inheritance directly to define variations of behavior, like the template method pattern, while others use it to create extensible families of objects. Polymorphism. Many forms, one interface. The word polymorphism comes from Greek, meaning many forms. In OOP, polymorphism is the ability of objects of different classes to be treated as objects of a common type. This means you can write code that operates on a general type, and that code will automatically work with any specific subtype, because the general type can take on many forms. Consider a universal remote control. You press the power button. While the physical button is the same, the actual action it performs might differ significantly depending on whether you're controlling a TV, a DVD player, or a stereo receiver. The power command takes on many forms in its execution. Why it matters for patterns. Polymorphism is at the heart of flexible and extensible design. It allows for dynamic behavior changes without modifying the client code. Many behavioral patterns, such as strategy, state, or command, rely entirely on polymorphism to swap different algorithms or states interchangeably. Abstraction. Focusing on the essentials. Abstraction is the process of simplifying a complex system by focusing on its essential features while hiding unnecessary details. It's about providing a generalized, high-level view. Think of a map. It shows you the major roads and landmarks, abstracting away the countless individual houses, trees, or specific cracks in the pavement. You get the essential information you need for navigation without being overwhelmed by minutiae. Why it matters for patterns. Patterns are, by their very nature, abstract solutions. They define roles and collaborations between general entities, not concrete, specific implementations. Abstraction allows these patterns to be applicable across a wide variety of contexts and specific domains, promoting reusability of design. The solid principles. Guidelines for robust design. Beyond the core pillars, a set of 5 design principles, collectively known by the acronym SOLID, provide further guidance for writing maintainable and extensible object-oriented software. These principles were popularized by Robert C. Martin and are highly relevant to understanding why patterns are structured the way they are. Single Responsibility Principle, SRP, idea. A class should have only one reason to change. This means each module or class should be responsible for one specific piece of functionality. Why it matters. Classes with a single responsibility are easier to understand, test, and maintain. If a change request comes in, you know exactly which class needs modification. Many design patterns help enforce SRP by distributing responsibilities among multiple, focused objects. Open-closed principle OCP. Idea, software entities, classes, modules, functions, etc. should be open for extension, but closed for modification. This means you should be able to add new functionality without changing existing, well-tested code. Why it matters. OCP is crucial for creating systems that are robust against change. If you have to modify existing code every time you add a new feature, you risk introducing bugs into stable components. Many patterns, especially behavioral ones like strategy or template method, are direct applications of OCP, allowing new behaviors to be added via new classes without altering existing ones. Liskov substitution principle, LSP. Idea. Subtypes must be substitutable for their base types without altering the correctness of the program. If Class B is a subtype of Class A, then anywhere Class A is used, Class B should be usable instead without problems. Why it matters. LSB ensures that inheritance hierarchies are well-formed and that polymorphic behavior works reliably. If a subclass behaves inconsistently with its parent type, it can lead to unexpected errors. This principle reinforces the importance of carefully designed relationships in patterns that utilize inheritance. Interface segregation principle, ISB. Idea. Clients should not be forced to depend on interfaces they do not use. Many client-specific interfaces are better than one general-purpose interface. Why it matters. Large, fat interfaces can lead to unnecessary dependencies, where a class has to implement methods it doesn't need, or clients have to know about methods they don't care about. ISB encourages breaking down interfaces into smaller, more focused ones. This leads to more flexible and robust designs, reducing coupling and making systems easier to refactor, a concept often seen in patterns where specific roles implement specific, minimal interfaces. Dependency inversion principle, DIP. Idea, high-level modules should not depend on low-level modules. Both should depend on abstractions. Abstractions should not depend on details. Details should depend on abstractions. Why it matters. This is perhaps one of the most powerful principles for building flexible architectures. Instead of a high-level module, like a payment processor, directly depending on a low-level module, like a credit card reader, they both depend on an abstraction, an iPayment device interface. This allows you to easily swap out different payment devices without changing the high-level logic. Many patterns, particularly creational and structural ones, inherently apply DIP by introducing interfaces that decouple components and promote flexibility. Composition over inheritance, a powerful design approach. While inheritance is a fundamental OOP concept, a guiding principle in modern object-oriented design is to prefer composition over inheritance. Composition means building complex functionality by assembling simpler objects. Instead of a car being a kind of engine and a wheel, which doesn't make sense, a car has an engine, has wheels, and has seats. The car class contains instances of engine, wheel, and seat objects. Why it matters, flexibility. Composition allows for more flexible designs. You can change the behavior of a composed object at runtime by swapping out its constituent parts. For example, a car could switch between a gasoline engine and an electric motor at design time simply by having a different engine object. Reduced coupling. Components are less tightly coupled than with inheritance. You change the internal behavior of a component without affecting the container. Avoids the gorilla banana problem. As put by Joe Armstrong, the creator of Erlang. The problem with object-oriented languages is they've got all this implicit environment that they carry around with them. You wanted a banana, but what you got was a gorilla holding the banana and the entire jungle. With inheritance, when you inherit behavior, you often get a lot of other behaviors and data that you don't need or want. Composition allows you to pick and choose exactly the functionality you need. Many of the structural and behavioral patterns, such as decorator, adapter, and strategy, are prime examples of applying composition to achieve flexible and extensible designs. Conclusion: object-oriented design patterns are not standalone mystical constructs. They are clever, refined ways to apply these fundamental object-oriented principles: encapsulation, inheritance, polymorphism, abstraction, the solid principles, and the preference for composition to solve specific, recurring design problems. As we delve into individual patterns in the following chapters, always keep these core principles in mind. They are the why behind the what. Understanding them will enable you to not just memorize pattern structures, but to deeply comprehend their purpose, recognize new opportunities to apply them, and even intelligently adapt them to your unique challenges. With this foundation, you are now ready to explore the exciting world of creational patterns and learn how to craft objects with precision and care. Chapter 3: The Builder Pattern. Constructing complex objects step by step. We begin our exploration of creational patterns, and the first one on our journey is the builder pattern. As the name suggests, this pattern is all about constructing something, particularly when that something is complex and involves multiple steps or specific configurations. Imagine you're at a sandwich shop, but not just any sandwich shop, a gourmet one. You don't just ask for a sandwich. Instead, you specify exactly what you want. I'd like sourdough bread, toasted, with roasted turkey, Swiss cheese, lettuce, tomato, a touch of mustard, and no pickles. Each choice is a step in the building process, and the order or combination of these choices defines your unique sandwich. If you then told your friend, "Build me one just like that, but add avocado," the process remains the same, but the final outcome is slightly different. Now, consider building something even more complex, like a custom computer system. You don't just say, "Give me a computer." You detail the central processing unit, the amount of random access memory, the type of graphics card, the storage solution, the case, the cooling system, and so on. The process of putting all these components together is intricate, and combining them in different ways results in entirely different machines. A high-end gaming rig versus a basic office workstation. Trying to specify all these choices in a single request or within a simple function call would be overwhelming. This is precisely the kind of problem the builder pattern aims to solve. The core problem the builder pattern addresses is this: how do you construct a complex object step by step, such that its construction process is independent of its parts and their assembly? In other words, when an object has many optional parameters or configurations, and its creation process is complicated, how do you manage that complexity clearly and flexibly? Why and when to use it? Motivation and applicability. The builder pattern is most beneficial in scenarios where the construction process is complex and sequential. The object needs to be built in a specific order or through a series of distinct steps, where each step might involve specific logic or configurations. You want to separate the construction logic from the object's representation. You might have a standardized way of building something, e.g., assemble a car, but you want to produce different end products, e.g., a luxury car versus a basic car, using that same assembly process, just with different parts or features. The object's constructor would become unwieldy. If your object requires dozens of parameters, many of which are optional or depend on other parameters, trying to cram all this into a single constructor leads to what's known as a telescoping constructor. This is a constructor with an ever-increasing number of parameters to accommodate different combinations, making it difficult to use and understand. A helpful analogy for the builder pattern is a master chef and their specialized cooks. The master chef, the director, knows the recipe for a complex dish, the sequence of steps. First prepare the dough, then the sauce, then the toppings, then bake. However, the master chef doesn't actually make the dough or the sauce themselves. Instead, they instruct different specialized cooks, the concrete builders. One cook knows how to make thin crust dough and another knows deep dish dough. The master chef can use either of these cooks to get their specific type of dough. Each cook handles the details of their specific part and eventually provides the finished dish. This allows the master chef to create many variations of the same fundamental dish, say, pizza, by simply swapping out the specialized cooks without changing the core recipe steps. Structure, abstracted description for audio. The builder pattern typically involves 4 main roles. The product, this is the complex object that you want to build. It's the sandwich or the computer system. It doesn't need to know anything about how it's built, only what its final state is. The builder, This is an interface or an abstract blueprint for building the product. It declares the common steps required to construct the product, for example, add bread, add meat, add cheese, get finished product. It's like the general instructions for building any sandwich. Concrete builders. These are the specific implementers of the builder interface. Each concrete builder knows precisely how to perform each building step to create a specific version of the product. For instance, a gourmet sandwich builder would put together a sandwich with artisan ingredients, while a fast food sandwich builder might use simpler components. Crucially, each concrete builder also holds onto the finished product and provides a method to retrieve it once construction is complete. The director. This role is optional but very common and useful. The director knows the exact sequence of building steps required to construct a particular configuration of the product. It takes a builder, one of the concrete builders, then tells it, step by step, to perform the necessary construction methods. The director doesn't know how each step happens, only what steps need to be taken and in what order. The overall flow is like this. Someone, often referred to as the client, decides they need a complex object. They create a specific concrete builder for the type of object they want. If a director is used, the client also creates the director and hands it the concrete builder. The director then orchestrates the construction by calling the appropriate building methods on the concrete builder in the correct sequence. Once all the steps are completed, the client asks the concrete builder to hand over the fully assembled product. Participants, roles defined. Builder, abstract builder, declares an abstract interface for creating parts of a product object. Concrete builder implements the builder interface and constructs and assembles parts of the product. It provides a means for retrieving the product. Director constructs an object using the builder interface. It's responsible for the overall algorithm of construction. Product, the complex object under construction. Collaborations, how they interact. A client creates a director object and a concrete builder object. The client tells the director which concrete builder to use for construction. The director then calls the building methods on the provided concrete builder in the specified sequence to construct the parts of the product. The concrete builder performs the actual work of building parts and assembling them into the product it manages internally. Once the construction process is complete, perhaps signaled by the director or by the client deciding all necessary components are added, the client retrieves the final product from the concrete builder. Consequences, pros and cons. Advantages, separates construction from representation. This is the most significant benefit. The director or client only cares about the sequence of building steps, build part A, build part B, not about the internal details of how those parts are created or how they contribute to the final product. The concrete builder, on the other hand, knows the specifics of creating and assembling parts for a particular product version. This means you can change how a product is built without affecting the code that uses the product or the director that orchestrates the overall process. Fine-grained control over construction. You have precise control over each step of the object's creation, allowing for highly configurable products. Each part can be built and configured independently before being assembled. Supports variation in product construction. By simply substituting different concrete builder implementations, the same director or construction process can create vastly different variations of the same type of product, e.g., a standard car versus a luxury car. Cleaner constructors eliminates the need for telescoping constructors with many optional parameters, leading to cleaner and more readable client code. Disadvantages, trade-offs, increased complexity. For simple products, introducing the builder interface, concrete builders, and an optional director can add unnecessary overhead and classes, making the design more complex than a straightforward constructor or factory method. Initial setup overhead. Setting up the builder pattern requires more upfront design and coding than a simple direct instantiation. It's best suited for situations where the complexity justifies this overhead. Implementation, considerations, and variations. Omitting the director. While the director is helpful for encapsulating common construction algorithms, it's not strictly necessary. For simpler needs, the client can directly interact with the concrete builder to call its building methods in any desired sequence. The director is a specialization for when you have several standard product configurations or a complex, fixed building process. Fluent interface, method chaining. A common stylistic choice for builder implementations is to have the building methods of the concrete builder return the builder object itself, this in many languages. This allows for method chaining, creating highly readable creation code like builder set engine, V8, set wheels, 18, set color, red, build. Immutability. The builder pattern is an excellent way to construct immutable objects. Since the object is built step by step internally within the concrete builder and only returned as a fully constructed, unmodifiable product at the end, its state cannot be altered afterward. Related patterns. Abstract factory. While both builder and abstract factory are creational patterns, they serve different purposes. An abstract factory focuses on creating families of related objects without specifying their concrete classes. A builder focuses on constructing a single, complex object step by step. Sometimes, an abstract factory might return a builder object, or a builder might use an abstract factory to create its complex parts. Composite. The builder pattern is often used to construct complex tree-like structures, which are typical applications of the composite pattern. The builder iterates through nodes, adding components to the composite structure. Factory method. The factory method creates a single object, often based on a simple input parameter, using an interface for deferring instantiation to subclasses. The builder offers a much more controlled and step-by-step approach for highly complex object creation, where the object has many parts and configurations. The builder pattern helps us manage the complexity of creation, separating the concerns of how something is built from what is being built. It promotes flexible designs where construction processes can be varied without altering the client code that orchestrates the building or the final product itself. Armed with this pattern, we can now move on to other creative approaches for object instantiation, delving next into the factory method. Chapter 4. The Factory Method Pattern. Letting subclasses decide. In the previous chapter, we explored the builder pattern, a powerful tool for constructing complex objects step by step. Now, we shift our focus to another foundational creational pattern, the factory method. While the builder manages intricate construction sequences, the factory method addresses a different but equally common problem: how to create objects without explicitly specifying their exact class. Imagine you are running a successful logistics company that specializes in delivering goods. Your fleet includes various types of vehicles: trucks for heavy cargo, vans for express delivery, and even drones for lightweight, urgent packages in urban areas. When a new delivery order comes in, you don't want the dispatch system to directly decide and create a new truck, or new van, or new drone every time. This would tie your dispatch logic tightly to the specific vehicle types. What if you add a new vehicle type, like an autonomous delivery robot? You'd have to painstakingly update every part of your dispatch system that creates vehicles. The core problem the factory method pattern solves is: how can an object creation process be deferred to subclasses, allowing a class to create various types of objects without exposing the instantiation logic to the client? It's about letting a class decide which specific product to create, enabling flexibility and reducing coupling between the creator and the concrete product classes. Why and when to use it, motivation and applicability. The factory method pattern is particularly useful in situations where a class cannot anticipate the class of objects it must create. The creator needs to work with several kinds of products, but it doesn't know upfront which specific subclass of product it will need. This could be due to configuration, runtime conditions, or future extensibility. A class wants its subclasses to specify the objects it creates. When you design a framework or a library, you often want to provide a common interface for operations that involve creating objects, but you want to give users of your framework the flexibility to define their own specific objects. You want to centralize object creation. Even if you know the exact type of object, centralizing creation in a factory method can make it easier to manage instantiation logic, apply common configurations, or change the default type later. Consider a digital document editor. You might have various types of documents: text documents, spreadsheets, presentations. When a user chooses New Document, the application doesn't directly create new text document or new spreadsheet. Instead, it asks a document creator to produce a new document instance. The document creator knows how to instantiate the correct document type based on user selection or predefined settings. If a new document type is introduced later, e.g., a mind map document, you extend the document creator and its subclasses rather than modifying existing creation points throughout the application. A good analogy for the factory method is a post office with different service counters. You go to the post office because you need to send something, a product. You don't care how the actual sending object, e.g., a letter, a parcel, a registered mail item, is created or handled internally. You go to a specific counter, the creator factory method, say the parcel post counter, and you describe what you need to send. That counter is responsible for handling the specifics of creating and processing your parcel. If you pick a different counter, say registered mail, it will create and process a different type of mail item. The post office itself doesn't directly create your mail item. Its specialized counters do, deciding which item to produce based on their type and your request. Structure, abstracted description for audio. The factory method pattern typically involves two parallel hierarchies. Product hierarchy. Product, abstract product. This is an interface or abstract class defining the common operations for the objects the factory method creates. It's like the general concept of a vehicle or document. Concrete products. These are the actual implementations of the product interface. For example, truck, van, drone for vehicle, or text document, spreadsheet for document. Each concrete product knows how to perform the operations defined by product. Creator hierarchy. Creator, abstract creator. This is an abstract class or interface that declares the factory method, a method responsible for returning an object of type product. The creator may also define other operations that use the product object. Crucially, the creator leaves the actual instantiation of the concrete product to its subclasses. Concrete creators. These are the subclasses of creator. Each concrete creator implements the factory method to return a specific concrete product. For example, a trucking company, concrete creator, might implement the method to produce trucks, while a drone delivery service, concrete creator, produces drones. The flow of control is simple. A client interacts with the creator or one of its concrete creators. When the client needs a product, it invokes the factory method on the creator. The creator, specifically its concrete creator subclass, then instantiates and returns the appropriate concrete product object. The client receives a product object, but it doesn't need to know the specific concrete product class that was instantiated. Participants, roles defined. Product, abstract product. An interface or abstract class defining the type of objects the factory method creates. Concrete product. A concrete implementation of the product interface, which the factory method will instantiate. Creator, abstract creator. Declares the factory method, which returns an object of type product. It may also define other methods that use the product. Concrete creator. Implements the factory method to return an instance of a concrete product. Collaborations, how they interact. The client code interacts with the creator class or one of its concrete creator subclasses. When the client needs a product object, it calls the factory method on the creator. The concrete creator's implementation of the factory method is responsible for instantiating the appropriate concrete product and returning it. The client receives a product object, typically through its abstract interface, and can then use it, unaware of its specific concrete class. Consequences, pros and cons. Advantages, decouples creator from concrete products. The creator class no longer needs to know the specific concrete product classes it creates. This eliminates the need for conditional logic, like if else or switch statements, that would otherwise be needed to decide which product to instantiate. Open-closed principle. New concrete products can be introduced without modifying the existing creator or client code. All you need to do is create a new concrete product class and an associated concrete creator class, extending the system rather than changing it. Centralized creation logic. Even if no new product types are anticipated, Using a factory method centralizes the object creation logic. This makes it easier to manage how objects are instantiated, potentially apply decorators, or add logging around the creation process. Customization by subclassing. The pattern provides hooks for subclasses to customize the type of product that will be created. Disadvantages trade-offs, increased number of classes. Introduces parallel class hierarchies, product and creator, which can sometimes lead to a proliferation of classes, especially for simpler use cases. For every new concrete product, you typically need a corresponding new concrete creator. Complexity for simple cases. For a very simple scenario where only one type of product is ever needed, the pattern can introduce needless complexity and abstraction. Implementation, considerations, and variations. Parameterized factory method. Sometimes, a single creator class might have a factory method that takes a parameter, e.g., a string or an enum, to decide which concrete product to instantiate. While this is technically still a factory method, it deviates from the canonical GoF sense of deferring to subclasses. Such an approach often uses a large switch statement internally and is sometimes referred to as a simple factory or static factory, and might lead to a violation of the open-closed principle if new product types require modifying the switch statement. The pure GoF factory method prefers separate concrete creator classes for each concrete product. Abstract creator or interface. The creator can be either an abstract class with an abstract factory method or an interface if the language supports default methods. The factory method name. The method can be named anything, though common conventions include create product type, make product type, or simply factory method. Related patterns. Abstract factory. The abstract factory pattern is often implemented using a set of factory methods internally. While factory method focuses on creating a single product, abstract factory focuses on creating families of related products. Builder. As discussed, builder focuses on step-by-step construction of a single complex object, whereas factory method focuses on deferring the choice of product type to subclasses. Template method. The creator class in the factory method pattern often defines a template method that uses the factory method as a hook to produce a product. The template method defines the overall algorithm, while the factory method allows subclasses to plug in their specific product creations. The factory method pattern stands as a cornerstone of extensible and maintainable object-oriented design. By abstracting the instantiation logic, it empowers you to create flexible systems that can easily adapt to new product types without disrupting existing code. It's a powerful testament to the principles of polymorphism and the open-closed principle, allowing your code to evolve gracefully. From creating documents to managing game characters, the factory method offers a refined approach to object creation, setting the stage for even more sophisticated creational patterns, which we will explore next with the abstract factory. Chapter 5, the abstract factory pattern, families of related objects. In our journey through creational patterns, we've learned how the builder pattern meticulously constructs single, complex objects step by step, and how the factory method pattern defers the decision of which single product to create to subclasses. Now, we expand our scope to a pattern designed for a slightly more elaborate scenario, the abstract factory pattern. This pattern tackles the challenge of creating a family of related objects without specifying their concrete classes. Imagine you're an interior designer furnishing a new home. You don't just need a chair, a table, and a sofa. You need a set of furniture that adheres to a specific style, perhaps modern, Victorian, or Art Deco. It would be incredibly cumbersome and prone to error if you had to meticulously select each piece of furniture individually, hoping they all matched the chosen style. What if you accidentally picked a Victorian chair to go with a modern table? Instead, what you need is a reliable source that guarantees all the items you acquire from it belong to the same consistent theme. You might go to a modern furniture emporium and request a chair, a table, and a sofa. You trust that everything you get from this specific emporium will be consistently modern in style. If your client then decides they want a Victorian theme instead, you simply switch to a Victorian furniture emporium and request the same types of items, knowing that emporium will provide consistently Victorian pieces. This scenario perfectly illustrates the problem the abstract factory pattern solves. How can you ensure that a system creates families of related or dependent objects that are all consistent with a particular theme or configuration, without needing to specify their concrete classes upfront? It's about providing an interface for creating related objects, letting concrete implementations of that interface handle the specifics of producing consistent families. Why and when to use it, motivation and applicability. The abstract factory pattern is a powerful tool in situations where your system needs to be independent of how its products are created, composed, and represented. Your core application logic shouldn't care if it's dealing with a Windows-style button or a macOS-style button. It just needs a button. Your system needs to be configured with one of multiple families of products. This is the core strength. You can easily swap entire sets of related objects, like changing a UI theme or switching a database vendor. A family of related product objects is designed to be used together, and you need to enforce this constraint. The pattern guarantees that, when you ask for multiple objects from a specific factory, they will always be compatible and belong to the same set. You want to provide a library of products, but only reveal their interfaces, not their concrete implementations. This keeps the client code clean and focused on common behaviors, not specific details. Consider a cross-platform user interface, UI toolkit. Your application needs to run on Windows, macOS, and Linux and look native on each. So when your application asks for a button, a checkbox, or a window, it doesn't want a generic one. It wants a Windows button, a macOS checkbox, and a Linux window, respectively. The choice of which operating system's UI elements to use is a configuration that affects an entire family of UI controls. The abstract factory ensures that if you get a Windows button, you'll also get Windows checkboxes and Windows windows from the same source. Structure, abstracted description for audio. The abstract factory pattern revolves around two main groups of components: the factories themselves and the products they create. Abstract factory. This is an interface or an abstract blueprint for creating abstract products. It declares a set of methods, one for each type of product in the family you want to create. For our furniture example, this might be an iFurniture factory with methods like create chair, create table, and create sofa. Concrete factories. These are the actual implementations of the abstract factory interface. Each concrete factory corresponds to a specific family or theme of products. So, you would have a modern furniture factory, a Victorian furniture factory, and an Art Deco furniture factory. Each of these factories would implement create chair, create table, and create sofa, but they would return their respective style of chair, table, and sofa. Abstract products. These are interfaces or abstract classes for each type of product that can be created. For our furniture, we would have iChair, iTable, and iSofa. These define the common behaviors for all chairs, tables, and sofas, regardless of their style. Concrete products. These are the specific implementations of the abstract product interfaces. They are the actual objects that the concrete factories instantiate. Examples include modern chair, Victorian chair, Art Deco sofa, etc. Each concrete product belongs to a specific family and implements its corresponding abstract product interface. Client. The client code is the part of your application that needs to use these product families. Crucially, the client only uses the abstract factory interface and the abstract product interfaces. It never directly deals with the concrete factories or concrete products. It's like the interior designer only knowing they need a chair and understanding what a chair does without caring if it's a specific modern chair class. The overall process is like this. At some high-level point in your application, perhaps at startup or based on user configuration, you decide which specific concrete factory, e.g., modern furniture factory, to use. You create an instance of that concrete factory. From that point onward, whenever your client code needs a piece of furniture, it asks this specific factory for it, e.g., current factory create chair, and the factory guarantees to provide a product consistent with its family. Participants, roles defined. Abstract factory declares an interface for operations that create abstract product objects, e.g., furniture factory, concrete factory, implements the operations to create concrete product objects. Each concrete factory corresponds to a specific family or theme, e.g., modern furniture factory, Victorian furniture factory. Abstract product declares an interface for a type of product object, e.g., chair, table, sofa. Concrete product defines a product object to be created by the corresponding concrete factory. Implements the abstract product interface, e.g., modern chair, Victorian chair. Client uses interfaces declared by abstract factory and abstract product classes. Does not know the concrete classes that are being produced, only their abstract types. Collaborations, how they interact. The client determines which concrete factory family it needs. This decision is typically made once, perhaps based on configuration options, user preferences, or the operating environment. The client then instantiates that specific concrete factory, e.g., new modern furniture factory. Whenever the client needs a product from that family, it calls the appropriate creation method on the abstract factory interface, e.g., factory create chair. The concrete factory implementation produces the corresponding concrete product that belongs to its specific family and returns it, e.g., the modern furniture factory's create chair. Method returns a modern chair. The client interacts with the returned product using its abstract product interface, completely unaware of its concrete type. This maintains a high degree of decoupling. Consequences, pros and cons. Advantages. Enforces consistency among products. This is the most significant benefit. It guarantees that all products created from a particular factory instance belong to the same family or theme. You won't accidentally mix a Windows button with a Mac OS menu if you consistently use the correct factory. Isolates concrete classes from client code. The client code deals only with abstract interfaces, abstract factory, and abstract product. It knows nothing about the concrete classes that are actually instantiated. This makes the client code extremely flexible and decoupled, allowing easy swapping of entire product families. Ease of swapping product families. To change the entire look and feel of your UI or switch databases, you typically only need to change a single line of code at your application's initialization point, the line that instantiates the concrete factory. All other client code remains unchanged. Consistency with open-closed principle for families. New families of products, e.g., an industrial furniture theme, can be introduced easily by creating a new concrete factory class and its corresponding concrete product classes without modifying any existing client code or existing factories. Disadvantages, trade-offs. Difficulty adding new product types. This is the main drawback. If you need to add a new kind of product to your family, e.g., you decide furniture now needs lamps in addition to chairs, tables, and sofas, you must modify the abstract factory interface itself to add a new create lamp method. Consequently, every single concrete factory implementation, modern, Victorian, Art Deco, must then be updated to include an implementation for creating lamps. This violates the open-closed principle for adding new product types. Increased complexity. The pattern introduces a notable number of interfaces and classes, abstract factory, multiple concrete factories, multiple abstract products, multiple concrete products. For systems with only one product family or few product types, this can be overkill and add unnecessary complexity without providing sufficient benefit. Implementation considerations and variations. Factory method as a building block. The abstract factory pattern often uses factory methods internally. Each method on the abstract factory, e.g., create chair, create table, can be seen as its own factory method that produces a specific type of product. So, while factory method creates one type of product, abstract factory creates families of products by composing several factory methods. Singleton for the concrete factory. Since you typically only need one instance of a particular concrete factory at any given time, e.g., only one modern furniture factory for the current configuration, the concrete factory itself is often implemented as a singleton pattern. We will discuss the singleton pattern in detail in a later chapter. Balancing extensibility. If you anticipate frequent additions of new types of products, not just new families, you might consider combining abstract factory with other patterns like prototype or a more dynamically configurable factory mechanism to reduce the impact of adding new product types. Usage with configuration. The selection of which concrete factory to instantiate at the beginning of an application is often driven by external configuration files, ensuring flexibility without recompiling code. Related patterns. Factory method. As highlighted, abstract factory is frequently implemented as a collection of factory methods, one for each type of product in the family. It's a higher-level pattern that coordinates the creation of multiple related objects. Builder. While both are creational, they solve different problems. Builder focuses on step-by-step construction of one complex product, like assembling a car with many configurable parts. Abstract factory focuses on creating families of related products, like ensuring all parts of a car match a luxury or economy theme. Singleton. A concrete factory is commonly implemented as a singleton to ensure only one instance of the factory exists for a given product family. Bridge. The bridge pattern is also about separating an abstraction from its implementation. An abstract factory can be used to create the concrete implementations that the bridge pattern uses. For instance, an abstract factory might provide the specific UI rendering implementations that a bridge pattern then uses to draw generic shaped buttons across platforms. The abstract factory pattern provides a powerful way to manage the creation of multiple, related objects, ensuring consistency and promoting architectural flexibility. It allows your system to be easily reconfigured to work with different themes or styles of components without altering your core application logic. As we move forward, we will continue to explore other patterns that streamline object creation, bringing us closer to mastering the art of elegant software design. Chapter 6, The Prototype Pattern, Cloning Your Way to New Objects. We've now explored patterns that help us build complex objects step by step, builder, and those that delegate object creation decisions to subclasses or families, factory method, abstract factory. Now, let's delve into another powerful creational pattern, the prototype pattern. This pattern offers a unique approach to object creation, allowing you to create new objects by simply copying an existing one without needing to know its exact type. Imagine you're a sculptor working with a rare and valuable material. You've painstakingly crafted a magnificent and intricate statue. Now, your client wants several more copies of this exact statue, perhaps with minor variations. Would you start from scratch each time, carving every detail anew? That would be incredibly time-consuming, expensive, and prone to errors. Instead, a much more efficient approach would be to make a mold of your original masterpiece. With that mold, you can quickly cast multiple identical copies. You can then take those copies and, if needed, make minor modifications or paint them differently. In software, creating new objects can sometimes be as complex and resource-intensive as hand sculpting. Some objects might require a complicated initialization process, perhaps involving reading from databases, configuring network connections, or performing extensive calculations. Direct instantiation, using a keyword like new in many programming languages, would mean repeating this expensive setup every time. Furthermore, sometimes you don't even know the concrete class of the object you need to create until runtime. The core problem the prototype pattern addresses is this: how can you create new objects by copying an existing object without being coupled to the specific class of the object you're copying? It's about leveraging the process of cloning or copying an existing instance rather than instantiating a new one from scratch. Why and when to use it, motivation and applicability. The prototype pattern is particularly well suited for situations where object creation is expensive or complex. If building an object from scratch involves numerous steps, heavy computations, or external resource access, cloning an existing, fully initialized object can be significantly more efficient. You need to create many objects that are slight variations of each other. Instead of creating each variant from scratch, you clone a master object and then make the necessary small adjustments. Think of a graphics editor where you might create many shapes that are almost identical, just differing in color or size. You want to decouple the client code from the concrete classes of objects it creates. The client interacts only with an abstract prototype interface, asking it to clone itself. It doesn't need to know or specify the exact concrete class being copied. This gives your system the flexibility to add new product types just by registering new prototypes. Avoiding parallel class hierarchies. In contrast to the abstract factory or factory method patterns, where you might have parallel hierarchies of factories corresponding to product hierarchies, prototype can sometimes simplify this by allowing an object to clone itself. A fitting real-world analogy is a photocopier or a 3D printer. You don't build a new document or object from raw materials every time you need a copy. Instead, you feed an existing document into a photocopier, and it produces an exact copy. With a 3D printer, once you have a digital model, your prototype, you can print as many physical replicas as you need. The machine knows how to replicate the form, and you can take a replicated object and perhaps paint it a different color or add a minor accessory after it's produced. Structure, abstracted description for audio. The prototype pattern involves a few key participants. The prototype, abstract prototype. This is an interface or an abstract class that declares a method for cloning itself. This method is typically named clone or copy. It's like the instruction manual for any object that knows how to duplicate itself. Concrete prototypes. These are the actual classes that implement the prototype interface. Each concrete prototype knows how to copy its own instance to produce a new object that is an exact replica. For example, a circle class and a rectangle class might both be concrete prototypes, each knowing how to create a new circle or rectangle identical to itself. Client. This is the code that needs to create new objects. Instead of creating objects directly using concrete constructors, the client obtains a reference to an existing prototype object, then simply calls clone on that prototype. The client receives a new object, which is now a copy of the original. The simplified flow is, a client asks an existing object, the prototype, to make a copy of itself. The prototype performs the internal work of constructing the new identical object and hands it back to the client. The client can then use this new object as is or modify it slightly to create a variant. Participants, roles defined. Prototype, abstract prototype, declares an interface for cloning itself. Concrete prototype implements the clone operation defined in the prototype interface. It is responsible for making an exact copy of its own instance. Client creates new objects by asking a prototype to clone itself. Collaborations, how they interact. The client holds a reference to an existing prototype object, or an interface it implements. When the client needs a new object that is similar to the prototype, it calls the clone method on the prototype instance. The concrete prototype, the object being cloned, then executes its clone method. This method takes all the values from its own properties and initializes a new object with those same values. In many programming languages, this involves creating a new instance of its own class and copying the internal state. The new, cloned object is returned to the client. The client can then independently use or modify the state of this newly created object, knowing it started as an exact copy of the original prototype. Consequences, pros and cons. Advantages, reduced subclassing. Unlike factory method or abstract factory, you don't need a separate concrete creator class for each type of product you want to create. You just provide a concrete prototype instance to clone. This keeps the class hierarchy flatter. Runtime flexibility. New types of objects can be added to the system simply by registering new concrete prototype instances. The client code doesn't need to change. This allows for highly dynamic systems that can be extended at runtime. Reduced configuration complexity. For objects that are slight variations of existing objects, it's often much simpler to clone an existing object and modify a few properties than to construct a new object from scratch using a complex constructor with many parameters. Performance benefits. When object creation is computationally expensive, e.g., database access, network calls, cloning an existing cached or partially initialized object can be significantly faster than repeated fresh instantiation. Disadvantages, trade-offs. Complexity of cloning complex objects, deep versus shallow copy. This is the most significant challenge. If a concrete prototype contains references to other objects, i.e., it has a complex internal structure or object graph, implementing a correct clone operation can be tricky. Shallow copy. Often, the default cloning mechanism in a language performs a shallow copy, meaning it copies the references to other objects, not the objects themselves. This can lead to unexpected side effects. If the original object and its clone both hold a reference to the same subobject, modifying that subobject through one will affect the other. Deep copy. A deep copy recursively copies all referenced objects, ensuring that the cloned object is completely independent of the original. Implementing a deep copy can be complex, especially with circular references, and might require custom serialization/deserialization or recursive copying logic. Overhead for simple objects. For objects that are simple to create using standard constructors and don't need runtime flexibility or performance optimization, the overhead of implementing the clone method might be unnecessary, cluttering the code. Loss of object identity, sometimes. If the very identity of an object is crucial, e.g., it represents a unique database record, cloning can sometimes be problematic if not handled carefully, as the clone is a distinct object even if its initial state is identical. Implementation, considerations, and variations. Language-specific cloning. Different programming languages have different built-in mechanisms for cloning. For example, Java uses the clonable interface and the object clone method, which performs a shallow copy by default. C# provides clonable. Python's copy module offers copy.copy, shallow, and copy.deepcopy. Deep. Understanding these language specifics is crucial. The prototype manager registry. Often, in a system using the prototype pattern, you'll find a centralized prototype manager or registry. This is typically a map or dictionary that stores various concrete prototype instances, indexed by a key, e.g., a string name or an ID. The client can then request a prototype by its key and clone it. Shape clone shape equals prototype manager get, red circle, clone. This manager simplifies client access and allows for dynamic registration and unregistration of prototypes at runtime. Parameterized cloning. While the basic idea is a direct copy, some advanced implementations might allow passing parameters to the clone method to indicate specific modifications to be applied during the copying process, resulting in a slightly preconfigured clone. Related patterns. Abstract factory/factory method. The prototype pattern can often serve as an alternative to abstract factory or factory method, especially when the system should be independent of how its products are created, and when new product types are introduced by registering prototype instances. In some cases, an abstract factory might even use prototype to implement its factory methods. Composite. When dealing with composite structures, objects composed into tree-like structures, cloning entire composite objects often requires a deep copy implementation within the concrete prototype's clone method to ensure the new composite structure is independent of the original. Memento. While memento is a behavioral pattern, it shares a conceptual similarity in that it involves saving and restoring object state. A memento might internally use a prototype to create a copy of an object's state. The prototype pattern offers a powerful, flexible, and often performant way to create new objects based on existing ones. It reduces coupling, enhances runtime extensibility, and can simplify code for objects with complex construction. However, its effectiveness hinges on careful consideration of shallow versus deep copy, a crucial detail in implementation. With cloning abilities now understood, we move to our final, and perhaps most talked about, creational pattern. The singleton. Chapter 7, the singleton pattern, ensuring one and only one. We've explored several fascinating ways to create objects, from step-by-step construction builder to deferring creation choices, factory method, abstract factory, and even cloning existing instances, prototype. Now, we arrive at a creational pattern that stands apart due to its unique principle, the singleton pattern. This pattern is designed to ensure that a class has only one instance and provides a single, global point of access to it. Imagine a country's head of state, say, the president or prime minister. At any given moment, there is only one person holding that office. There cannot be two or more presidents governing the same country simultaneously. It would lead to chaos, conflicting directives, and a breakdown of governance. Everyone in the country and indeed, the world knows how to contact or interact with the office of the president. There's a single, well-known point of access, such as the White House in the United States or 10 Downing Street in the United Kingdom. In software, there are many situations where a single point of control or a unique resource manager is absolutely essential. For instance, consider a central logging service for an application. If multiple independent logging instances could freely write to the same log file, their operations might conflict, messages could be interleaved incorrectly, or the file could even become corrupted. Or think about a configuration manager that loads application settings from a single file. Having multiple instances of this manager, potentially reading from different versions of the configuration or holding conflicting settings in memory, would lead to unpredictable and erroneous behavior across your application. The core problem the singleton pattern addresses is this. How do you guarantee that a class has only one instance throughout an application's lifecycle and provide a global, well-known point of access to that single instance? It's about ensuring uniqueness and providing controlled access. Why and when to use it, motivation and applicability. The singleton pattern is particularly applicable when there must be exactly one instance of a class, and it must be accessible from a well-known access point. This is its primary and defining purpose. The sole instance needs to be extensible by subclassing, and clients should be able to use an extended instance without modifying their code. This is a more advanced use case, implying that the singleton's access method can dynamically determine which specific subclass to instantiate based on configuration. This is less common in typical singleton implementations. Common scenarios for using the singleton include logger, a single logging facility that writes messages to a central log file or console. Configuration manager, an object that loads and manages application settings from a single source. Printer spooler, a single manager for all print jobs, ensuring they are queued and processed systematically. Database connection pool, a single point of control for managing and handing out database connections to prevent the creation of too many connections. Structure, abstracted description for audio. The singleton pattern achieves its goals by carefully controlling the instantiation process within the class itself. It typically involves these elements. Private constructor. The constructor of the singleton class is declared as private. This is the crucial step that prevents any other part of the program from directly creating instances of the singleton using the new keyword. It's like the rules of government, stating that only internal processes can create a precedent. Private static instance variable. The singleton class holds a private, static variable that will eventually store the single instance of itself. Being static means it belongs to the class itself, not to any particular object, and being private means it can only be accessed from within the singleton class. Initially, this variable is often null or uninitialized. Public static access method. The singleton provides a public static method, commonly named getInstance, createInstance, or instance. This is the only way for other parts of the program clients to get a reference to the singleton object. The mechanics of the getInstance method are as follows. When getInstance is called for the very first time, it checks if the private static instance variable is null, meaning no instance has been created yet. If it is null, getInstance proceeds to create the single instance of the singleton class using its private constructor and assigns it to the static instance variable. Any subsequent call to getInstance will find the static instance variable already populated. Instead of creating a new object, it simply returns the already existing instance. The result is that no matter how many times you call singleton getInstance, you will always receive a reference to the exact same single singleton object. Participants, roles defined. Singleton, the class that ensures only one instance of itself exists and provides a global access point to that instance. It typically has a private constructor and a public static method for retrieving the instance. Collaborations, how they interact. The client needing the singleton instance calls its public static access method, e.g., singleton getInstance. The singleton's access method checks if its internal sole instance has already been created. If the instance does not exist, The access method creates it internally using its private constructor. The access method then returns the one and only instance to the client. Consequences, pros and cons. Advantages: guaranteed single instance. This is the pattern's primary strength. It ensures that only one instance of the class ever exists, preventing conflicting operations or managing unique resources. Controlled access to the sole instance. Unlike a simple global variable, which can be reassigned anywhere, the singleton provides a tightly controlled point of access through its getInstance method. This allows for lazy initialization, creating the instance only when it's first needed, and can incorporate specific initialization logic, logging, or security checks. Reduced namespace pollution. It avoids cluttering the global namespace with numerous global variables, which can lead to naming conflicts and make dependencies less clear. While a singleton effectively acts global, its access mechanism is more structured. Flexibility through subclassing with care. As mentioned, the getInstance method can be designed to return an instance of a subclass, allowing the application to switch concrete singleton implementations at runtime. However, this often adds significant complexity and is not a common reason to use singleton. Disadvantages: trade-offs, tight coupling, and global state. This is the most significant criticism and major drawback. A singleton often introduces global state into an application. This makes the code harder to understand, debug, and test, as any part of the application can potentially modify the singleton state, leading to unpredictable side effects. Components become tightly coupled to the singleton. Testability challenges. Due to its global nature and fixed instance, replacing a singleton with a mock or substitute for isolated unit testing can be very difficult. Since you can't simply new up a different version, tests might interfere with each other or require complex setup teardown. This makes testing classes that depend on singletons harder. Concurrency issues, multi-threading. Implementing a singleton correctly in a multi-threaded environment requires careful thought. Without proper synchronization mechanisms, like locking or careful memory management, multiple threads could simultaneously try to create the instance, leading to multiple singleton objects being created, violating the pattern, or other race conditions. Misuse and anti-pattern potential. The singleton is one of the most frequently misused patterns. It's often applied simply for global access when a simpler approach, like dependency injection or passing objects explicitly, would be more appropriate and lead to more flexible, testable code. When a singleton accumulates too many responsibilities, it can evolve into an God object or Swiss Army knife, violating the single responsibility principle. Many experienced developers advise against using the singleton unless there is an absolute, unavoidable need for a truly global, single instance. Implementation considerations and variations. Lazy versus eager initialization. Lazy on demand. The instance is created only when getInstance is called for the very first time. This saves resources if the singleton might not always be needed. This is the most common approach. Eager at startup. The instance is created immediately when the class is loaded, even if it's not used right away. This is simpler to implement and inherently thread-safe without explicit locking, but resources might be allocated unnecessarily. Thread safety for lazy initialization. For lazy initialization in multi-threaded environments, you must ensure thread safety. Synchronized method. Synchronizing the entire getInstance method is simple, but can cause performance bottlenecks if getInstance is called frequently after the instance is created. Double-checked locking. A common optimization attempt for thread-safe lazy initialization. It involves checking for null twice, once without a lock and once with a lock, and only locking the actual creation. However, it's notoriously tricky to implement correctly across different programming languages and memory models, and often buggy. Initialization on demand holder idiom. Often used in Java, this is generally considered the safest and most efficient way to achieve lazy, thread-safe singleton in many languages without explicit locking, by relying on internal class loading mechanisms. Enum-based singletons. Especially in Java, a powerful, simple, and inherently thread-safe way to implement singletons that also protects against serialization issues and reflection attacks. Serialization issues. If a singleton needs to be serializable, deserializing it can inadvertently create a new instance, violating the pattern. Special methods, like readResolve in Java, are required to intercept this and return the existing single instance. Reflection attacks. In some programming languages, reflection can bypass private constructors, potentially allowing unauthorized creation of multiple instances. Defenses usually involve adding a check within the private constructor to throw an exception if an instance already exists. Related patterns. Abstract factory/factory method. These patterns can leverage a singleton to ensure that there is only one instance of the factory itself, especially if the factory is a central component for creating families of related objects. State/strategy. The context class in a state or strategy pattern might itself be a singleton if it manages a globally unique state or strategy. Facade. A facade often itself is a singleton, providing a simplified, single point of access to a complex subsystem. The singleton pattern, while seemingly straightforward in its intent, is arguably the most debated and frequently criticized design pattern. Its tendency to introduce global state and complicate testing means it should be used with extreme caution, and only when there is a truly compelling and unavoidable need for a single, globally accessible instance. Alternative approaches like dependency injection often provide more modular and testable solutions for managing single instances of a service. Understanding when not to use a pattern is as important as knowing when to use one. With the singleton, we conclude our exploration of creational patterns. We've learned how to carefully control object creation, from complex step-by-step assembly to flexible family generation, and the strict enforcement of uniqueness. Next, we will move into the world of structural patterns, where we'll discover how to compose classes and objects to form larger, more flexible structures. Chapter 8, the adapter pattern, bridging incompatible interfaces. We now transition from creational patterns to structural patterns. While creational patterns focus on how objects are instantiated, structural patterns are concerned with how classes and objects are composed to form larger structures. Our first stop in this category is the adapter pattern, a pattern dedicated to enabling existing systems to work together despite initial incompatibilities. Imagine you're traveling internationally, perhaps from a country that uses Type A electrical outlets, those with 2 flat parallel pins, to a country that uses Type G, 3 rectangular pins, like in the UK. You've brought your trusty laptop, but its power adapter has a Type A plug. Clearly, you can't just jam your plug into a Type G socket, they are physically incompatible. You have 2 perfectly functional devices, your laptop charger and the wall socket, but they can't communicate electrically. What do? You buy a travel adapter. This small, ingenious device plugs into the wall socket, conforming to the Type G interface, and provides an opening where you can plug in your laptop charger, exposing a Type A interface. The travel adapter doesn't change your laptop charger, nor does it rewire the building's electricity. It simply acts as a mediator, translating the electrical interface from one form to another, allowing 2 previously incompatible entities to work together seamlessly. In the world of software, we face similar interface mismatches all the time. You might have a well-established, perhaps legacy, software component or a third-party library that performs a specific task absolutely perfectly. Let's say it's a powerful and efficient old data processor. However, its method names and the way it expects data are completely different from what the rest of your modern application expects from a data processing component, which might be looking for an iData Analyzer interface. You can't or don't want to modify the old data processor's source code, yet you need its functionality. This is the core problem the adapter pattern addresses. How do you make 2 distinct components or classes, which were designed independently and thus have incompatible interfaces, work together without modifying their original code? It's about translating one existing interface into another interface that a client expects. Why and when to use it, motivation and applicability. The adapter pattern is invaluable in situations where you want to use an existing class, but its interface doesn't match the one you need. This is the classic scenario of integrating a legacy component or a third-party library into a modern system. You want to create a reusable class that cooperates with unforeseen or unrelated classes. For example, you might design a sophisticated reporting engine that needs to pull data from various sources, databases, web services, local files. Instead of making the reporting engine tightly coupled to each data source's specific interface, you define a common iData source interface and write adapters for each specific data source, transforming their native interfaces into the iData source interface. You are designing a general-purpose toolkit or framework, and you need to provide a unified interface for a set of classes with varying specific interfaces. The beauty of the adapter pattern lies in its ability to facilitate interoperability and reuse. It acts as a bridge, allowing components from different contexts to collaborate without requiring deep modifications or breaking existing contracts. Structure, abstracted description for audio. The adapter pattern typically involves 4 main roles. The target interface. This is the interface that your client code expects and wants to use. It defines the operations and methods that the client understands. For our power adapter example, this would be the shape of the wall socket in the new country. In software, it might be an interface like iData Analyzer with a method like analyze, data set data. The client. This is the part of your application that needs to perform an operation and expects to interact with an object through the target interface. It doesn't know about or care about the adaptee's incompatible interface. The adaptee. This is the existing class or component that actually does the useful work, but it has an interface that is incompatible with the target interface. This is your laptop charger with its specific plug type, or the old analytics tool with its send event, event type, string payload method. The adapter. This is the core of the pattern. It's a class that implements the target interface, so it looks like what the client expects. Internally, the adapter holds a reference to an instance of the adaptee. When the client calls a method on the adapter, using the target interface, the adapter translates that call into one or more calls to the adaptee's incompatible methods. It performs the necessary conversion of arguments or method names. Think of it as a language translator. The client speaks one language, the target interface. The adaptee speaks another, its native interface. The adapter understands both languages. When the client tells the adapter something in its language, the adapter processes it, translates it into the adaptee's language, tells the adaptee, and then translates the adaptee's response back to the client. Participants, roles defined. Target, the interface that the client expects and operates against. Client, the object that makes requests using the target interface. Adaptee, the existing class whose interface needs to be adapted. It contains the desired functionality, but in an incompatible form. Adapter, the class that implements the target interface and contains an instance of the adaptee. It is responsible for translating method calls from the target interface to the adaptee's interface. Collaborations, how they interact. The client makes a request to the adapter through the target interface. For example, data analyzer analyze, my data. The adapter receives this request. The adapter then translates the request. It extracts the necessary information from the target method call and converts it into the format expected by the adaptee. It then makes the appropriate call or calls to the adaptee's specific, incompatible methods. For example, old tool.process data, my data to string, level high. The adaptee performs its operation and might return a result. The adapter may then optionally translate the adaptee's response back into the format expected by the target interface before returning it to the client. Consequences, pros and cons. Advantages, interoperability, the primary benefit. It allows existing, incompatible classes to work together seamlessly without modifying their source code. This is particularly valuable when dealing with legacy systems or third-party libraries where source code modification is not an option. Reusability promotes the reuse of existing components. Instead of rewriting functionality that already exists, you simply provide an adapter. Decoupling decouples the client from the implementation details of the adaptee. The client only interacts with the familiar target interface and doesn't need to know anything about the adaptee's idiosyncrasies. Flexibility. You can adapt the same adaptee to multiple different target interfaces or different adaptees to the same target interface as needed. Transparency. For the client, the adapter object looks and behaves just like any other object implementing the target interface. The adaptation is transparent to the client. Disadvantages trade-offs. Increased complexity. For very simple interface mismatches, introducing a new class, adapter, into the system can seem like overkill and might add unnecessary complexity. Overhead. There's a tiny performance overhead due to the extra layer of indirection. The method calls through the adapter and then to the adaptee. In most applications, this is negligible and far outweighed by the benefits of flexibility and reuse. Not a replacement for good design. While powerful for integration, the adapter pattern should not be used to justify or perpetrate bad initial design choices. It's a tool for retrofitting compatibility, not for designing new components with incompatible interfaces from the start. Implementation considerations and variations. The adapter pattern has two main forms, differing in how the adapter connects to the adaptee. Object adapter, using composition. This is the more common and generally preferred approach. The adapter class implements the target interface and contains an instance of the adaptee, composition. When a method is called on the adapter, it delegates the call to its contained adaptee object after any necessary translation. Benefits. More flexible. The adapter can work with any subclass of the adaptee, and even different adaptees as long as they can be adapted to the same target interface. It doesn't inherit unnecessary behavior from the adaptee, only exposes what's needed through the target interface. Class adapter, using inheritance. In languages that support multiple inheritance, like C++, the adapter class would inherit from the adaptee class and also implement the target interface. Benefits can be simpler to implement in some cases as it doesn't require explicit delegation. Drawbacks, less flexible. It ties the adapter to a specific adaptee subclass. If the adaptee is a class, the adapter inherits all its behaviors, which might not always be desirable, violating the interface segregation principle when the adaptee is large. It also requires multiple inheritance, which is not available in many popular languages like Java or C#. The choice between an object adapter and a class adapter often comes down to the specifics of the programming language and the degree of flexibility required. For generality and cleaner design, the object adapter composition is usually the go-to. Related patterns. Bridge. Both adapter and bridge patterns are concerned with decoupling interfaces or implementations, but they solve different problems and are used at different stages. The adapter changes an existing interface so it matches a required interface, often applied retrospectively to integrate existing components. The bridge separates an abstraction from its implementation so that both can vary independently during initial design, designed upfront for extensibility. Decorator. Both adapter and decorator, as well as proxy, which we'll discuss later, use composition to wrap an object. The key difference is their purpose. Adapter changes the interface of the object it wraps. It's about making an incompatible interface compatible. Decorator adds responsibilities to the object it wraps while maintaining the same interface. It's about enhancing functionality. Facade. Facade provides a simplified, higher-level interface to an entire subsystem of classes, making it easier to use. It doesn't change the interfaces of the existing classes within that subsystem. A facade might internally use an adapter if some classes within the subsystem have incompatible interfaces that need to be made consistent for the facade to work with them. The adapter pattern is a quintessential example of how object-oriented principles like abstraction and composition can be applied to solve practical, real-world problems in software integration. It empowers developers to build modular, maintainable systems by promoting the reuse of existing components, even if they weren't originally designed to work together. With this understanding of adapting interfaces, we can now move on to another structural pattern that offers even deeper levels of decoupling, the bridge pattern. Chapter 9, the bridge pattern. Decoupling abstraction from implementation. In the last chapter, we saw how the adapter pattern helps two incompatible interfaces work together. Now, we'll explore another powerful structural pattern, the the bridge pattern, which takes decoupling to a whole new level. While the adapter changes an existing interface, the bridge separates an abstraction from its implementation so that both can vary independently. This is a crucial distinction and makes the bridge a valuable tool for designing highly flexible and extensible systems. Imagine you are developing a drawing application that needs to support various shapes, circles, squares, triangles, and render them on different platforms, Windows, macOS, Linux, or using different rendering APIs, OpenGL, DirectX, SVG. If you were to approach this using traditional inheritance, you might quickly run into problems. You could have a base shape class and then subclasses like circle, square, triangle. But then, how do you handle the rendering? Do you create Windows circle, Mac OS circle, Linux circle, and then Windows square, Mac OS square, Linux square? This leads to a disastrous explosion of classes, a Cartesian product, number of shapes, number of platforms. Every time you add a new shape or a new platform, you have to create many new concrete classes. This is a maintenance nightmare. The core problem the bridge pattern solves is this. How do you break a direct, rigid connection between an abstraction, what something is, and its specific implementation, how it does what it does, allowing both to evolve and vary independently without affecting each other? It aims to prevent a class explosion and enable greater flexibility. Why and when to use it, motivation and applicability. The bridge pattern is particularly useful in situations where you want to avoid a permanent binding between an abstraction and its implementation. This means you want to choose or change the implementation at runtime. For the drawing app, you want to use a circle object, but decide at runtime if it's drawn with OpenGL or DirectX. Both the abstraction and its implementation should be extensible independently. Expanding the number of shapes should not necessitate changes in the rendering system, and vice versa. A change in the implementation of an abstraction should not require a change in the client code. The client only deals with the abstraction. You have a large number of classes resulting from a combination of two different dimensions of variation. This is the class explosion problem we discussed with shapes and renderers. You want to hide the implementation details from the client. The client should only interact with the high-level abstraction. A good real-world analogy for the bridge pattern is a universal remote control the abstraction and individual electronic devices, the implementations. A universal remote is designed to control various devices like a TV, DVD player, or stereo. The remote itself doesn't know the intricate details of how to change channels on each specific brand of TV. Instead, it sends abstract commands like power on or volume up. The actual work of interpreting these commands and manipulating the device is handled by internal IR, infrared, codes specific to each brand. This is the implementation. The remote can be configured to use different sets of IR codes, allowing it to bridge the gap between the abstract command and the concrete device implementation. You can get a new TV, a new implementation, and update the remote without changing the remote's core functionality or its buttons, the abstraction. Structure, abstracted description for audio. The bridge pattern achieves its flexibility by completely separating the abstraction, what the object does, from its implementation, how it does it. It introduces an interface for the implementation and a reference to that interface within the abstraction. Abstraction. This is the high-level control or interface for the functionality. It defines the abstract methods that the client will call. Importantly, it contains a reference, a bridge, to an implementer object. It delegates the actual work to this implementer object. For our drawing app, this might be a shape abstract class with methods like draw and resize. Refined abstraction. These are concrete classes that extend the abstraction. They provide specific variations of the high-level control. For example, circle, square, triangle would be refined abstractions, each inheriting the draw and resize methods and delegating them to their internal implementor. Implementor. This is an interface or abstract class that defines the methods for the underlying implementation. These are the primitive operations that the abstraction needs. For drawing, this might be iRenderer with methods like renderCircle, renderLine, setPenColor. Concrete implementor. These are the actual concrete classes that implement the implementor interface. They provide the actual lower-level code to perform the operations. For example, OpenGL renderer, DirectX renderer, SVG renderer. The crucial element is the abstraction holding a reference to the implementor. When a client calls a method on the abstraction, e.g., circle draw, the abstraction doesn't implement the drawing itself. Instead, it delegates that call to its associated implementor object, e.g., renderer render circle. Because the abstraction only knows about the implementor interface, it can be paired with any concrete implementor. Participants, roles defined. Abstraction defines the abstraction's interface, maintains a reference to an implementor object. Refined abstraction extends the abstraction interface by adding or refining abstract behaviors. Implementor defines the interface for implementation classes. This interface doesn't have to correspond directly to the abstraction's interface. It provides the primitive operations that the abstraction needs to implement its higher-level operations. Concrete implementor implements the implementor interface and defines its concrete implementation. Collaborations, how they interact. The client interacts with the abstraction or one of its refined abstraction subclasses. The abstraction delegates its client requests draw, resize, to its contained implementor object renderer. The implementor, OpenGL renderer, DirectX renderer performs the actual low-level operations. Crucially, the abstraction is unaware of the concrete implementor class. It only interacts with the implementor interface. The concrete implementor is unaware of the abstraction that might be using it. This complete separation allows both hierarchies to vary independently. Consequences, pros and cons. Advantages, decoupling, clearly separates the abstraction from its implementation. This is the primary strength. Changes to the implementation do not affect the client using the abstraction, and vice versa. Extensibility. Both the abstraction hierarchy, e.g., new shapes, and the implementation hierarchy, e.g., new renderers, can be extended independently without causing a class explosion. You add one new shape and one new renderer, not number of current shapes, number of new renderers, and vice versa. Flexibility allows the implementation to be configured or changed at runtime. A circle object can seamlessly switch between OpenGL renderer and DirectX renderer if required. Reduced class explosion eliminates the need for a combinatorial explosion of derived classes, which would occur if implementation were bound to abstraction through inheritance. Disadvantages trade-offs. Increased complexity introduces a relatively complex structure with multiple interfaces and classes. For very simple scenarios where the abstraction and implementation are highly stable or have a direct, unchanging relationship, this might be overkill. Initial design overhead requires careful upfront design to correctly identify the abstraction and implementation hierarchies and their interaction. It's a pattern you apply during design, not typically to refactor existing, tightly coupled code without significant effort. Implementation, considerations, and variations. Sharing implementors. A single concrete implementor instance might be shared by multiple abstractions if the implementation is stateless or thread-safe. Layering pimple idiom. The bridge pattern is sometimes referred to as a form of the handle body, or pimple, pointer to implementation, idiom in C++, where the handle is the abstraction and the body is the implementor. This technique is commonly used to hide implementation details and improve compile time dependencies. Configurability. The choice of concrete implementor for a given abstraction can be determined by configuration files, environment variables, or other dynamic means, allowing for highly configurable software. Related patterns. Adapter. Both adapter and bridge patterns are about connecting unrelated systems. However, their primary goals differ. Adapter makes existing things work together retrospectively by changing the interface of an adaptee to match a target interface. Bridge separates an abstraction from its implementation proactively during design, allowing them to vary independently from the start. Abstract factory. An abstract factory can be used to create and configure the concrete implementor objects that the abstraction will use. For example, a Windows widget factory might create a Windows renderer as one of its products, which could then be used by shape abstractions. Strategy. At first glance, bridge and strategy might seem similar because both use composition to delegate behavior. The key difference lies in their intent. Strategy allows an object's behavior to be chosen at runtime. It's about swapping algorithms. The client usually chooses the strategy. Bridge separates an abstraction from its implementation. It's about managing two independent dimensions of variation. The abstraction contains and delegates to the implementation. The bridge pattern is a sophisticated and powerful structural tool. It might seem complex at first, but its ability to untangle tightly coupled systems and foster independent evolution in two distinct dimensions makes it invaluable for building robust, scalable, and maintainable software architectures. By mastering the bridge, you gain a significant advantage in designing systems that can adapt and grow without succumbing to the dreaded class explosion. Next, we will explore the composite pattern, which helps us to treat individual objects and groups of objects uniformly. Chapter 10, The Composite Pattern, Trees of Objects, Part-Whole Hierarchies. In our exploration of structural patterns, we've seen how the adapter bridges incompatible interfaces, and the bridge decouples abstraction from implementation. Now, we turn our attention to the composite pattern, a powerful tool that allows you to treat individual objects and groups of objects uniformly. It's about building tree-like structures where you can apply operations across both individual components and compositions of components as if they were all the same type. Imagine you are developing a graphical drawing application. You can draw individual shapes like circles, squares, and triangles. But what if you want to group several shapes together, move them as one unit, resize them, or change their color? And what if you want to create groups of groups? For example, a house group might contain a wall group and a roof group, and the wall group might contain several brick shapes. Without the composite pattern, you'd face a dilemma. Your drawing functions would need separate logic for handling individual shapes versus handling groups of shapes. For instance, a draw method would have to check, am I drawing a single shape? Then draw it. Am I drawing a group? Then loop through its contents and draw each one. This conditional logic complicates the client code and makes it brittle. Adding a new type of group or a new shape would require modifying all drawing routines. The core problem the composite pattern solves is this. How do you represent part-whole hierarchies, where objects can be composed into tree structures, such that clients can treat individual objects and compositions of objects uniformly? It allows you to build complex structures from simpler ones, while making the client code that operates on these structures simpler and more generic. Why and when to use it, motivation and applicability. The composite pattern is particularly beneficial in situations where you need to represent a part-whole hierarchy of objects. This means data that naturally forms a tree structure, where individual items can also contain other items. Examples include file systems, files and folders, organizational charts, employees and departments, UI components, buttons, panels, windows, or network topologies. Clients should be able to ignore the difference between individual objects and compositions of objects. The core idea is that uniform treatment works best. If you can draw a single shape, you should be able to draw a group of shapes using the same method call, without needing to know if you're dealing with a single object or a collection. You want to make the structure of your system more flexible. Adding new types of components, either individual leaves or new kinds of composites, often doesn't require changing existing client code. A good real-world analogy for the composite pattern is a company organizational chart. An individual employee is a leaf component. A department, like sales or marketing, is a composite component as it contains many individual employees. An entire division, like North American operations, is also a composite component as it contains multiple departments. When the CEO, the client, asks everyone to submit their quarterly reports, they don't send emails to every single employee. They send the request to the heads of divisions, who then delegate to department heads, who then delegate to individual employees. Each step of the way, the submit report request is handled uniformly, regardless of whether it's an individual or a group. Structure, abstracted description for audio. The composite pattern typically involves three main roles. Component. This is the abstract base class or interface. It declares the interface for objects in the composition, both for individual objects, leaves, and for composite objects. It defines operations that are common to both. Crucially, it also declares methods for adding, removing, and retrieving child components, although these methods are typically implemented meaningfully only by composite objects. Leaf. This represents individual objects in the composition. Leaf objects do not have any children. They implement the component interface and define basic behavior. In our drawing example, circle, square, triangle would be leaf components. Composite. This represents components that can have children. It implements the component interface and stores leaf or other composite objects. It forwards operations to its children and often provides methods for managing children, like add, remove, getChild. In our drawing example, group would be a composite component. The structure forms a tree where composite nodes can contain both leaf nodes and other composite nodes. Participants, roles defined. Component. An abstract class or interface defining the common interface for both leaf and composite objects. It declares operations for manipulating children, e.g., add, remove, getChild, which may throw exceptions or do nothing in leaf components, indicating they don't support child operations. Leaf represents a primitive object in the composition. It has no children. It implements all operations declared in component. Composite represents a composite object in the composition. It stores child components, both leaf and other composite objects. It implements operations declared in component, usually by delegating them to its children. It also provides methods for managing children. Collaborations, how they interact. The client interacts with objects through the component interface, treating both individual leaf objects and composite objects uniformly. When an operation is called on a leaf, e.g., square draw, the leaf directly performs the operation. When an operation is called on a composite, e.g., group draw, the composite typically iterates over its children and delegates the same operation to each child, e.g., for each child in children. Child draw, this recursive delegation is what enables uniform treatment. Adding and removing children are handled by the composite object. Consequences, pros and cons. Advantages, unified interface. Makes client code simpler because it can treat individual leaf objects and composite objects uniformly. You write code that expects a component, and it doesn't need to differentiate. Easier to add new component types. New leaf or composite subclasses can be added without changing existing client code, adhering to the open-closed principle. As long as they implement the component interface, they can be integrated seamlessly. Flexible structure. Encourages the creation of complex, recursive structures that can represent natural hierarchies. Disadvantages, trade-offs. Overgeneralization/type safety loss, sometimes. The main drawback is that you might lose some type safety. Since the component interface must define methods for both leaf and composite objects, even if leaf objects don't support child operations, leaf components might end up implementing methods that are irrelevant to them or result in do-nothing or an unsupported operation exception. This can make it harder to catch certain errors at compile time. Design complexity. For simple, flat structures, introducing the full composite pattern might be overkill and add unnecessary design complexity. Implementation, considerations, and variations. Child management in component. A key design decision is whether the component interface should include child management operations, like add, remove. Safe approach, less type safe. Put add and remove in the component interface. This provides maximal transparency for the client. They can try to add remove components from any component, even a leaf, but leaf components would need to provide a default empty implementation or throw an exception, like unsupported operation exception. This is the common GoF approach. Transparent approach, more type safe, do not put add and remove in the component interface. Only the composite class would have these methods. This means the client code would need to cast a component to a composite to manage children, breaking complete uniformity but providing compile time type safety. The GoF pattern prioritizes transparency, so the safe approach with a component interface that includes child management is more typical. Parent reference. Sometimes, components, both leaf and composite, might maintain a reference to their parent. This can simplify traversal up the tree structure, but introduces the complexity of managing these references, e.g., preventing circular references, handling deletion. Recursion. Operations on composite objects are almost always implemented recursively, delegating to their children. Related patterns. Decorator, both composite and decorator, which we'll discuss next, use recursive composition to organize a tree of objects. However, their intents are different. Composite aggregates objects into a tree structure, allowing clients to treat individual objects and compositions uniformly. It's about building a part-whole hierarchy. Decorator adds responsibilities to individual objects dynamically and transparently, without changing their fundamental interface. Factory method, abstract factory, can be used to create the various leaf and composite objects that form the tree structure. Iterator. An iterator pattern can be used to traverse the components of a composite structure, allowing you to access all elements, leaves, and composites in a standardized way. Visitor. The visitor pattern, a behavioral pattern, is often used with composite structures to perform operations on the elements of the structure without polluting the component classes with new responsibilities. This is especially useful if you need to add many new operations to leaf and composite classes. The composite pattern simplifies client code, promotes flexibility, and helps to model complex hierarchical structures naturally. By providing a uniform interface for both individual objects and groups, it allows developers to build elegant and maintainable systems that can easily adapt to evolving requirements in tree-like data representations. With our ability to form object structures now understood, let's turn to how we can dynamically add responsibilities to these objects. The decorator pattern. Chapter 11, the decorator pattern. Adding responsibilities dynamically. In our exploration of structural patterns, we've learned how to bridge interfaces with the adapter and how to manage tree-like object hierarchies with the composite. Now, we delve into another powerful structural pattern, the decorator pattern. This pattern offers a flexible alternative to subclassing for extending functionality and allows you to add new responsibilities to individual objects dynamically, keeping their interfaces consistent. Imagine you've just ordered a simple black coffee. It's good, but you might want to enhance it. You could add milk, or sugar, or both, or perhaps flavored syrup and then whipped cream. Each addition changes the final drink's characteristics and price, without fundamentally changing the fact that it started as coffee. The beauty is that you can apply these additions, decorations, in almost any order and combine them in unique ways. The coffee remains the base, but its behavior, taste, calories is dynamically augmented. Typically, when we want to add new features or modify behavior in object-oriented programming, our first thought often goes to inheritance. If you have a coffee class and you want coffee with milk, coffee with sugar, and coffee with milk and sugar, you might think of creating subclasses. However, this approach quickly leads to a class explosion as the number of possible combinations grows. Adding a new decorator, say, whipped cream, would require creating coffee with milk and whipped cream, coffee with sugar and whipped cream, etc. This becomes a maintenance nightmare and violates the open-closed principle, because adding new functionality forces you to modify existing class hierarchies or create an unwieldy number of subclasses. The core problem the decorator pattern addresses is this: how do you add responsibilities to individual objects dynamically and transparently, without affecting other objects or creating an unmanageable subclass hierarchy? It allows for flexible and customizable enhancements to objects. Why and when to use it, motivation and applicability. The decorator pattern is particularly useful in situations where you want to add responsibilities to individual objects, not to an entire class hierarchy. You don't want all instances of coffee to always have milk, only specific instances should have it. You want to add responsibilities dynamically and reversibly. You might want to switch them on or off, or apply them incrementally. Extending functionality by subclassing is impractical or leads to a class explosion. If you need many independent extensions or combinations of extensions, subclassing quickly becomes unmanageable. A class's definition should remain unchanged for new features. The object needs to function as originally intended while having its behaviors extended. Think of it in a text editor. you have a text viewer component. You might want to add features like scroll viewer adds scroll bars, border viewer adds a border, or line number viewer adds line numbers. You want to be able to apply these features independently, in combination, and to specific text viewer instances, not to all text viewers by default through inheritance. Structure, abstracted description for audio. The decorator pattern typically involves four main participants. Component. This is the abstract base class or interface. It defines the interface for objects that can have responsibilities added to them. Both the concrete component and the decorator classes implement this interface. This is crucial for maintaining type compatibility. For our coffee example, this might be iCoffee with a method getCost and getDescription. Concrete component. This is the actual object to which responsibilities can be added. It implements the component interface. This is our basic coffee class. Decorator. This is an abstract class that implements the component interface. It maintains a reference, typically protected, to a component object. It wraps the component. The decorator also typically implements component methods by simply forwarding calls to its wrapped component. This acts as a base for all specific decorators. Concrete decorators. These are the actual classes that add new responsibilities. Each concrete decorator extends the decorator class and implements the component interface. It adds its specific behavior before or after delegating the call to the wrapped component, or even intercepts and modifies the result. For example, milk decorator, sugar decorator, whipped cream decorator. The key idea is that a concrete decorator always wraps a component, which can be a concrete component itself or another concrete decorator. This recursive nature allows you to stack multiple decorators, each adding its own layer of functionality. Participants, roles defined. Component, an interface or abstract class defining operations that concrete component and decorator objects must implement. Concrete component, the concrete class to which additional responsibilities can be attached. Decorator, an abstract class that maintains a reference to a component object and conforms to the component interface. It typically passes all requests to the wrapped component. Concrete decorator extends decorator and adds specific responsibilities to the component it wraps. Collaborations, how they interact. The client creates a concrete component instance, e.g., new basic coffee. The client then optionally wraps this concrete component with one or more concrete decorator instances. Each concrete decorator is initialized with the component it will wrap. For example, new milk decorator, new basic coffee. When the client calls an operation on the outermost decorator, e.g., milk coffee getCost, the call passes through the chain of decorator objects. Each concrete decorator adds its own behavior, e.g., adds the cost of milk, and then delegates the call to its encapsulated component. Eventually, the call reaches the innermost concrete component, which performs its base operation. Results are then passed back up the chain, potentially modified by each decorator. Consequences, pros and cons. Advantages, more flexible than subclassing. Allows responsibilities to be added and removed dynamically at runtime. Avoids the class explosion problem that arises from static inheritance when many combinations of features are needed. Avoids feature overload in core classes. Keeps the core concrete component class lean, focusing on its fundamental responsibilities. New features are added via separate decorator classes. Open-closed principle. You can extend the functionality of objects without modifying existing code, the component or existing decorators. You simply create new concrete decorator classes. Supports single responsibility principle. Each decorator class is responsible for one specific additional behavior, making it easier to manage and test. Disadvantages, trade-offs. Increased number of small objects. The pattern can result in a design with many small, similar objects, which might be harder to manage or understand for simple cases. Debugging can sometimes be more challenging as calls pass through multiple layers of decorators. Complexity for simple cases. For a straightforward scenario where only one or two fixed responsibilities are needed, inheritance might be simpler. Equality check issues. Checking the equality of two decorated objects can be tricky because they are wrapped in different decorator instances, even if the underlying concrete component is the same. Limited access to wrapped object. Since clients typically interact only with the outermost decorator through the component interface, accessing specific properties or methods of the innermost concrete component directly can be difficult without typecasting, which reduces flexibility. Implementation, considerations, and variations. Order of decorators. The order in which decorators are applied can sometimes matter, as each decorator builds upon the previous one's behavior. Think of compression decorator, encryption decorator data. The order of compression, then encryption, versus encryption, then compression, might yield different results or even be incorrect. Using inheritance for decorator and component. A common setup is for component to be an interface and decorator to be an abstract class that implements component and holds a component reference. Concrete decorators then extend decorator. Transparent versus opaque decorators. Transparent. All operations on a decorator mimic the interface of its component. This allows layering. Opaque. A decorator might introduce new operations that are not part of the component interface. This breaks the stacking and uniformity of calls somewhat, but might be necessary for specific, non-delegatable behaviors. The GoF pattern typically implies transparency. Related patterns. Adapter. Both adapter and decorator use composition, wrapping an object, to achieve their goals. However, adapter changes the interface of the wrapped object to match an expected interface, while decorator adds responsibilities while maintaining the same interface. Composite. Decorator can be seen as a degenerate composite where there is only one child. Both patterns use recursive composition to organize objects. Composite builds a tree of objects where individual items and groups are treated uniformly. Decorator focuses on adding single responsibilities to individual objects. Strategy. While decorator adds responsibilities, strategy allows an object's behavior algorithm to be chosen or swapped cleanly at runtime from a set of alternatives. Decorator focuses on layering features, strategy on choosing among different concrete implementations of a behavior. Proxy. Both decorator and proxy, which we will cover soon, wrap another object and implement the same interface. The difference lies in their intent. Proxy controls access to an object. Decorator adds responsibilities to an object. The decorator pattern is a beautifully elegant and flexible solution for extending object functionality without resorting to rigid inheritance hierarchies. It promotes modularity, adherence to the open-closed principle, and allows for dynamic and customizable behavior. It's a prime example of composition over inheritance in action, giving you fine-grained control over how responsibilities are attached to your objects. With our newfound ability to dynamically add features, let's explore how to simplify complex subsystems using the facade pattern. Chapter 12. The facade pattern. A simplified interface to complexity. Having learned how to adapt interfaces, adapter, decouple abstractions from implementations, bridge, manage hierarchical structures, composite, and dynamically add responsibilities, decorator, we now turn to the facade pattern. This pattern offers a straightforward, yet incredibly effective, way to manage complexity by providing a simplified, single interface to a larger, complex subsystem. Imagine you're trying to start a complex piece of machinery, say, a sophisticated coffee vending machine. Internally, this machine has numerous subsystems: a grinder, a water heater, a pump, a milk frother, a sugar dispenser, and perhaps a payment system. To make a cappuccino, you'd theoretically have to interact with each of these subsystems individually. Grind coffee beans, heat water to 90 degrees, pump hot water through coffee grounds, froth milk, and so on. This would be incredibly complicated and error-prone for the ordinary user. Fortunately, the machine provides a much simpler interface. A few buttons labeled espresso, latte, cappuccino, or hot water. When you press the cappuccino button, the machine orchestrates all the underlying complex operations behind the scenes. It performs a sequence of specific actions across multiple subsystems, but you, the user, are completely unaware of this internal complexity. You interact only with a simple, high-level interface. In software, large applications are rarely monolithic. Instead, they are typically composed of many interconnected modules, classes, and subsystems, each with its own intricate API. when other parts of the application or external clients need to use functionality from such a subsystem, they can face a bewildering array of classes and methods. This complexity can lead to code that is difficult to understand, hard to maintain, and prone to breaking changes within the subsystem. The core problem the facade pattern addresses is this: how can you provide a simple, unified interface to a complex set of classes in a subsystem, making it easier to use without hiding the full functionality of the underlying subsystem? It's about reducing complexity and improving clarity for clients who don't need to delve into the intricate details of a subsystem. Why and when to use it, motivation and applicability. The facade pattern is most useful in situations where you need to provide a simpler or more convenient interface to a complex subsystem. The subsystem is fully capable, but its complexity overwhelms typical clients. You want to decouple a client from the many components of a subsystem. This reduces dependencies and makes the system more modular. If the internal implementation of the subsystem changes, the client, interacting solely with the facade, often doesn't need to be updated. You want to layer your system. A facade can define an entry point to each layer, promoting a structured approach and preventing lower-level components from being accessed directly by higher-level clients. You want to provide a specific view or subset of operations for a particular client type. For instance, one facade could offer banking operations for a teller, while another offers a different set for an ATM. Consider a home theater system. Internally, it might consist of a television, a DVD player, an audio receiver, and a surround sound speaker system, each with its own complex set of interfaces and remote controls. A facade would be a single master remote or a home theater controller interface that offers simplified methods like watch movie, listen to music, or play game. When watch movie is called, the facade internally powers on the TV, switches to the correct input, turns on the DVD player, and sets the audio receiver to the right mode and volume. Structure, abstracted description for audio. The facade pattern typically involves two main roles. Facade. This is the single, simplified interface that stands in front of the subsystem. It holds references to the various components of the subsystem classes. It provides high-level, convenient methods that delegate calls to the appropriate objects within the subsystem. The facade itself does not add new functionality or behaviors, it merely streamlines existing ones. Subsystem classes. These are the multiple classes and objects that make up the complex subsystem. They perform the actual work. The facade interacts with these classes, but clients do not typically interact with them directly. Participants, roles defined. Facade provides a simplified, high-level interface to the classes in a subsystem, intercepts client requests, and delegates them to the appropriate subsystem objects. Subsystem classes, the collection of classes and objects that implement the subsystem's functionality. They are typically unaware of the facade and can be used directly by clients who need deeper interaction. Collaborations, how they interact. The client interacts solely with the facade object, making requests through its simplified interface, e.g., home theater watch movie, Interstellar. The facade object receives the request. The facade then takes on the responsibility of coordinating the request. It translates the high-level request into a series of more granular calls to the appropriate subsystem classes. The subsystem classes perform the actual work, completing their tasks. They typically pass results back to the facade, which might aggregate them before returning a consolidated result to the client. Crucially, clients who need to access the full, complex functionality of the subsystem can still do so by directly interacting with the subsystem classes. The facade simply offers a convenient shortcut for the most common use cases. Consequences, pros and cons. Advantages: simplifies client interface, reduces the complexity for clients by providing a clear, simple entry point to a complex subsystem. Decouples client from subsystem. The client depends only on the facade and not on the individual subsystem classes. This reduces coupling and makes the client code less sensitive to internal changes within the subsystem. Improved maintainability. Internal changes to the subsystem, e.g., refactoring classes, adding new intermediate components, are less likely to affect clients, as long as the facade's interface remains stable. encourages layering, helps to break a large system into layers. A facade can be the public API for each layer, enforcing communication through well-defined interfaces. Hides implementation details. Clients don't need to know the intricate details of how the subsystem works, only how to use the high-level facade methods. Disadvantages trade-offs. Can become a God object. If not designed carefully, the facade can accumulate too many responsibilities, becoming a monolithic God object that knows too much about the entire subsystem. This defeats the purpose of modularity. Limits flexibility, potentially. While simplifying, it might hide certain specialized functionalities offered by the subsystem. Clients needing that specialized access must bypass the facade and interact directly with the subsystem classes, which can somewhat undermine the simplification goal if that's a frequent need. Dependency on all subsystem classes. The facade itself might end up depending on nearly all classes within the subsystem, potentially creating a large dependency graph within the facade's implementation. Implementation, considerations, and variations. Singleton facade. A facade is often implemented as a singleton if there's no reason to have multiple instances of the simplified interface managing the same logical subsystem. This ensures a single global access point to the subsystem functionality. Multiple facades. A complex system might have multiple facades, each providing a different view or set of operations for different types of clients or use cases. For example, a user management facade and a report generation facade might expose different aspects of a larger business logic subsystem. Integrating with other patterns. A facade might internally use other patterns. For example, it could use a builder to construct complex objects needed by the subsystem or strategies to handle different internal algorithms. Not a replacement for good design. A facade helps in clarifying interactions with an already complex subsystem. It's not a substitute for proper subsystem design that should aim for cohesion and low coupling internally. It simply wraps and simplifies what's there. Related patterns. Abstract factory/factory method. These patterns can be used by a facade to instantiate the complex objects within its subsystem. A facade might provide a simple create report method that internally uses a factory method to produce the correct report object. Singleton. As mentioned, a facade is often implemented as a singleton to provide a single, global access point. Mediator. Both facade and mediator simplify interactions between classes. A facade provides a simplified interface to a subsystem, reducing client dependency on multiple subsystem classes. The calls are typically one way from client to facade to subsystem. A mediator centralizes communication between multiple interdependent objects, colleagues, preventing them from directly referencing each other. This is about managing peer-to-peer communication. Adapter. An adapter changes the interface of an individual class to match a client's expected interface. A facade provides a simplified interface to an entire subsystem of classes, not necessarily changing existing internal interfaces. An adapter might be used within a facade if one of the subsystem classes has an interface that needs adaptation before the facade can use it. The facade pattern is an unsung hero of software architecture. It's simple, elegant, and incredibly effective at transforming tangled complexity into manageable simplicity. By providing a clear boundary and a streamlined entry point, it significantly enhances the usability and maintainability of complex systems, making them approachable for new developers and more robust to internal changes. Next, we will explore a pattern that tackles another aspect of resource management, the flyweight pattern. Chapter 13, the flyweight pattern, sharing to save memory. We've now covered several structural patterns, focusing on how objects are composed for adaptability, adapter, bridge, composite, and simplification, facade, decorator. Now, let's delve into a truly fascinating one, the flyweight pattern. This pattern is all about optimizing memory usage and performance by sharing common state among a large number of objects. Imagine you're designing a word processor, and you need to display a very long document. This document contains thousands, perhaps millions, of individual characters. If each character on the screen were represented by a unique object holding its font, size, color, and actual character value, you would quickly exhaust your computer's memory. Most as in a document are displayed in the same font, size, and color, unless explicitly formatted differently. It would be highly inefficient to store this redundant information for every single object. Similarly, consider a game with millions of trees, particles, or repeating environmental assets. If each tree object stored its species, color, and texture independently, the game would grind to a halt. When you realize that the vast majority of characters or trees share identical properties, an opportunity for optimization arises. The core problem the flyweight pattern addresses is this: how can you support a large, fine-grained objects efficiently, especially when many objects share common state, to reduce memory consumption and improve performance? It's about externalizing and sharing the intrinsic, unchanging parts of an object's state. Why and when to use it, motivation and applicability. The flyweight pattern is particularly useful in situations where an application uses a huge number of objects. Huge often means hundreds of thousands to millions. The vast majority of an object's state can be made extrinsic, context-dependent, rather than intrinsic, inherent to the object. Intrinsic state is the unchanging, shareable data. Extrinsic state is the variable, context-dependent data that changes from one instance to another. Many groups of objects share a significant portion of their intrinsic state. The cost of creating and storing objects is high. Going back to our word processor example, intrinsic state shareable. The font family e.g. Arial, font size e.g. 12pt, font color e.g. black for a particular character. These properties are the same for all A's in Arial 12pt black. Extrinsic state, unique to each instance. The character's position on the screen x, y coordinates, its specific character value e.g. A, B, C. This data changes for every character instance. The flyweight pattern separates these two types of state. The flyweight object stores only the intrinsic state, and this object is shared among all instances that possess that identical intrinsic state. The extrinsic state is passed to the flyweight object as parameters when its methods are called, or managed by a separate client or context object. A real-world analogy for the flyweight pattern is pre-printed business cards that you personalize with a stamp. Imagine you need hundreds of business cards for different clients, but they all share the same layout, logo, background, and company details. Instead of printing entirely new cards for each client, you print a large batch of blank business cards with all the common information. This is your flyweight, the shareable, intrinsic part. Then, for each client, you stamp their specific name, phone number, and email onto the card. The unique name, number, and email are the extrinsic state passed in at the moment of use. You share one physical pre-printed card design, effectively saving on printing costs and storage for the common elements. Structure, abstracted description for audio. The flyweight pattern involves usually three main roles, plus an optional but common fourth. Flyweight, abstract flyweight. This is an interface or an abstract class that declares an interface for objects that can receive extrinsic state. It defines operations for the flyweight, which may take the extrinsic state as arguments. For our word processor, it might be an iCharacter interface with a draw, int x, int y, char value method. Concrete flyweight. These are the actual objects that implement the flyweight interface. They store only the intrinsic, shareable state. Each concrete flyweight instance represents a unique combination of intrinsic properties. For example, a character flyweight instance would represent Arial 12pt black. Unshared concrete flyweight, optional. Some subclasses of flyweight might not be shareable if they have no intrinsic state to share, or if their extrinsic state has a complex relationship with the intrinsic state. These are less common within the pure flyweight context. Flyweight factory. This acts as a centralized repository for creating and managing concrete flyweight objects. Clients request flyweights from this factory. The factory checks if a concrete flyweight with the requested intrinsic state already exists. If so, it returns the existing instance. Otherwise, it creates a new one, stores it, and then returns it. This ensures that concrete flyweights are shared. Client context. The client creates and manages the extrinsic state information. It requests flyweight objects from the flyweight factory, and passes the unique extrinsic state to the flyweight operations when they are performed. Participants' roles defined. Flyweight declares an interface for objects that can receive and act upon extrinsic state. Concrete flyweight implements the flyweight interface and stores intrinsic state. Must be shareable. Unshared concrete flyweight optional. Not all flyweight objects need to be shared. If some instances contain state that is always unique, they can be unshared concrete flyweights. Flyweight factory creates and manages flyweight objects, ensures that flyweight objects are shared properly. Client maintains references to flyweight objects and computes or stores the extrinsic state of flyweights. Collaborations, how they interact. The client needs an object that performs a certain operation. Instead of creating a new object, it contacts the flyweight factory, providing the specific intrinsic state, e.g., Arial 12PT black, that it needs. The flyweight factory looks up its pool of existing concrete flyweight objects. If a concrete flyweight with that specific intrinsic state already exists, the factory returns it. If not, the factory creates a new concrete flyweight, stores it in its pool, and then returns it. The client receives a flyweight object. When it wants to perform an operation, e.g., draw, it passes the unique extrinsic state, e.g., the character's position x, y, and its actual character value, a, as arguments to the flyweight's method. The flyweight uses its intrinsic state and the provided extrinsic state to perform the operation. Consequences, pros and cons. Advantages, memory footprint reduction, the most significant benefit. By sharing common intrinsic state among many objects, the pattern dramatically reduces the total memory consumed by the application, especially when dealing with millions of objects. Performance improvement. Lower memory consumption can lead to better cache utilization and overall faster execution, as the application spends less time swapping data in and out of memory. Reduced object creation overhead. Since objects are retrieved from a factory instead of being created anew, the overhead of repeated object instantiation is minimized. Disadvantages trade-offs. Increased complexity. Introduces a layer of complexity due to the separation of intrinsic and extrinsic state and the need for a flyweight factory. This can make the code harder to understand initially. Runtime cost for extrinsic state. Each time a flyweight operation is invoked, the extrinsic state needs to be passed as parameters. This can introduce a minor runtime overhead compared to directly accessing an object's internal state, though this is usually negligible compared to the memory savings. Not always applicable. The pattern is only beneficial when the application needs a very large number of objects, and a significant portion of their state can be made extrinsic. If the intrinsic state is unique for most objects, or if the number of objects is small, the overhead of the pattern might outweigh its benefits. Implementation considerations and variations. Immutability of intrinsic state. It's crucial that the intrinsic state stored in concrete flyweight objects is immutable. If it could be changed by one client, that change would unexpectedly affect all other clients sharing the same flyweight instance. Factory as a singleton. The flyweight factory is often implemented as a singleton pattern, ensuring a single centralized point for managing flyweight objects. Context objects. Sometimes, the extrinsic state itself can be encapsulated in separate context objects, and these context objects could hold references to the flyweights. The client then interacts with the context objects. No unshared concrete flyweights. It's possible to implement the pattern without unshared concrete flyweights if all flyweights are truly shareable. Related patterns. Factory method, abstract factory. A flyweight factory is essentially a specialized factory that ensures object sharing. It uses a factory method, or abstract factory if it creates families of flyweights, to produce and manage its flyweight objects. Singleton. The flyweight factory itself is often a singleton to provide a single, well-known access point for retrieving shared flyweight objects. State/strategy. The context classes in state or strategy patterns sometimes store the extrinsic state and use a flyweight object to carry out operations based on that state. Composite. Composite objects often manage the extrinsic state of leaf components, and those leaf components could be implemented as flyweights if they are numerous and share intrinsic state. For example, a graphic object in a document, the composite, might manage the position, extrinsic state of many character objects, flyweights. The flyweight pattern is a powerful optimization technique. It's a brilliant solution for memory management and performance tuning in situations involving massive numbers of similar objects. While it adds a layer of complexity, the benefits in specific use cases can be dramatic, allowing applications to handle scaled data sets that would otherwise be impractical. With this unique approach to object sharing, we've nearly completed our exploration of how objects are structured and composed. Our final structural pattern will explore how objects can act as stand-ins for others. The proxy pattern. Chapter 14, The Proxy Pattern, a stand-in for the real thing. We've now covered most of the structural patterns, learning how to adapt incompatible interfaces, decouple abstractions from implementations, manage complex hierarchies, simplify subsystems, and even optimize memory usage by sharing objects. Our final stop in this category brings us to the proxy pattern. This pattern provides a surrogate or placeholder for another object to control access to it. It acts as a stand-in for the real object, allowing you to add various functionalities without altering the original object's code or the client's interaction with it. Imagine you're running a highly exclusive art gallery. You have a magnificent, incredibly valuable painting on display. It's too precious to be exposed to every visitor all the time. Instead, you could have a high-quality photograph or replica of the painting, a proxy, on display for most visitors. Only highly vetted, serious buyers or critics are granted access to view the actual, original masterpiece. The replica serves as a stand-in, managing and controlling access to the true work of art, perhaps even offering additional services like detailed descriptions or background information that are available to all, without needing to retrieve the original. In software, similar scenarios arise. You might have an object that is very expensive to create, access, or operate. Perhaps it's a large image that takes a long time to load from disk, a remote service that requires network calls, or a database connection that needs authentication. If every client that needs to interact with this real object directly creates or accesses it, your application could become slow, consume excessive resources, or run into security issues. The core problem the proxy pattern addresses is this: how can you provide a substitute or placeholder for another object to control access to it and potentially add additional functionality or improve performance without altering the client code that interacts with the real object? It's about managing access and adding services around an existing object. Why and when to use it, motivation and applicability. The proxy pattern is useful in many contexts, particularly when you need to control access to an object. This could involve security checks, lazy initialization, logging, caching, or remote access. Creating the real object is resource-intensive. If the object is costly in terms of memory, CPU, or network calls, you might want to defer its creation until it's absolutely necessary, lazy initialization. You need to add before and after logic to method calls. This includes logging, performance monitoring, or transaction management around the real object's operations. You need to provide a local representative for an object in a different address space. This is common in distributed systems, remote proxy. Different kinds of proxies serve different purposes. Remote proxy provides a local representation for an object that resides in a different address space, e.g., on a remote server. It handles the communication details behind the scenes. Virtual proxy acts as a placeholder for an object that is expensive to create. It defers the creation and initialization of the real object until it's actually needed, loading it on demand. This is useful for large images, complex reports, or heavy database objects. Protection proxy controls access to the real object based on permissions or security credentials. It acts as a gatekeeper, granting or denying access to certain operations. Smart reference proxy provides additional functionality when an object is accessed. This could include counting references to the object, tracking its use, or locking the object to prevent concurrent access. Cache proxy stores the results of operations performed by the real object, returning cached results for subsequent identical requests instead of calling the real object again. A real-world analogy for a virtual proxy could be a librarian providing a reference to a rare book. When you ask for a rare book, the librarian doesn't immediately hand you the physical artifact. Instead, they give you a reference card or tell you where it is, or perhaps provide a digital scan. The actual book is only retrieved from a climate-controlled vault, expensive access, if you truly need to inspect the original for research, true access. For most purposes, the reference or scan, the proxy, is sufficient, saving the effort and risk of handling the delicate original. Structure, abstracted description for audio. The proxy pattern typically involves three main roles. Subject, abstract subject. This is an interface or abstract class that defines the common interface for both the real subject and the proxy. This is crucial. The proxy and the real subject must be interchangeable from the client's perspective. It's like the artwork interface, with methods like display or getDetails. Real subject. This is the actual object that the proxy is representing. It contains the core business logic or sensitive data that needs controlled access. It implements the subject interface. This is the original painting. Proxy. This is the stand-in object. It implements the subject interface, just like the real subject. The proxy holds a reference to a real subject instance. When a client calls a method on the proxy can perform its additional logic, e.g., check permissions, lazy load, log the call before or after delegating the actual work to the real subject. Participants, roles defined. Subject, an interface or abstract class that defines the common operations for both the real subject and the proxy. Clients interact with this interface. Real subject, the actual object that performs the core task. It implements the subject interface. Proxy maintains a reference to a real subject object. It implements the subject interface, allowing it to be substituted for the real subject. The proxy controls access to the real subject and can perform additional logic before or after forwarding requests to the real subject. Collaborations, how they interact. The client makes a request to the proxy object using the subject interface, e.g., artwork display. The proxy receives the request. Based on its type, the proxy then performs its specific service. A virtual proxy might check if the real subject has already been created. If not, it creates it before delegating the call. A protection proxy might check client permissions. If the client is authorized, it delegates. Otherwise, it throws an error or denies access. A remote proxy might serialize the request and send it over the network to the real subject on another machine. A cache proxy might check if the result is already in memory and return it directly. Otherwise, it delegates and stores the result. After or before its service, the proxy delegates the original request to the real subject, e.g., real painting display. The real subject performs the actual operation and returns a result to the proxy. The proxy might process this result, e.g., log it, deserialize it, before returning it to the client. Crucially, the client is often unaware it's interacting with a proxy rather than the real subject, thanks to the common subject interface. Consequences, pros and cons. Advantages, controlled access. Provides a controlled and managed way to access the real subject. Lazy loading optimization. Virtual proxies can significantly improve application performance and resource usage by deferring the creation of expensive objects until they are actually needed. Security. Protection proxies can enforce access controls, ensuring only authorized clients can interact with the real subject. Logging monitoring. Smart reference proxies can transparently add logging, performance monitoring, or other audit capabilities around existing objects. Separation of concerns. The proxy handles concerns like security, logging, or caching, keeping the real subject focused on its core business logic. Remote object management. Simplifies interaction with objects located in different processes or network locations. Disadvantages trade-offs. Increased complexity. Introduces an additional layer of indirection, adding a new class, proxy, and potentially more complexity to the system. For simple object access, this might be overkill. Performance overhead. While virtual proxies can improve perceived performance, the additional layer of indirection, the proxy doing its work before delegating, can introduce a minor runtime overhead. this is generally negligible compared to the benefits gained. Client code impact, less common. If the proxy changes the behavior of the real subject in a way that isn't transparent, e.g., adding a significant delay not expected by the client, it can cause issues. The principle is that the proxy should be a transparent stand-in. Implementation considerations and variations. Dynamic proxies. Many modern languages provide mechanisms, e.g., reflection proxies in Java, proxy objects in JavaScript, to create proxies dynamically at runtime without having to write a separate proxy class for each real subject. This is particularly useful for concerns like logging, caching, or security, where the proxy's behavior is generic regardless of the real subject's specific methods. This forms the basis of aspect-oriented programming, AOP. Subject as a concrete class. While typically subject is an interface or abstract class for maximum flexibility, in some cases, the real subject itself might be a concrete class that the proxy directly extends. If the language allows and it makes sense, though composition is generally preferred. This is less common in pure GoF pattern usage. Related patterns. Adapter. Both adapter and proxy wrap an object. Adapter changes the interface of the wrapped object to match an expected interface. Proxy provides the same interface as the wrapped object, but adds a level of indirection to control access or add supplementary behavior. Decorator. Similar to proxy in that both wrap an object and implement the same interface. The difference is their intent. Proxy is about controlling access to an object or providing a substitute. The client might not even know or care if it's interacting with the real subject or a proxy. Decorator is about adding responsibilities functionality to an object dynamically and transparently without altering its core interface. Facade. A facade provides a simplified interface to a subsystem of classes. A proxy provides a surrogate for an individual object. A facade might contain a proxy if one of its internal components needs access control. Singleton. A protection proxy could potentially use Singleton to manage a single authorization manager that it consults. The proxy pattern is a foundational tool for managing object access and adding cross-cutting concerns cleanly. It empowers developers to build applications that are more efficient, secure, and robust by allowing them to separate infrastructural concerns from core business logic. With the proxy pattern concluding our tour of structural patterns, we now move into the final category, behavioral patterns, which focus on how objects interact and distribute responsibilities. Chapter 15. The Chain of Responsibility Pattern, Passing Requests Along a Chain. We now embark on our journey through behavioral patterns, the final category of the gang of 4 design patterns. These patterns focus on algorithms, communication, and the assignment of responsibilities between objects. Our first destination is the chain of responsibility pattern, a pattern that allows a request to be passed along a chain of handlers until one of them handles it. Imagine a customer service department in a large company. When a customer calls with an issue, they don't immediately get connected to the CEO. Instead, their call first goes to a frontline representative. If that person can resolve the issue, they do. If not, they escalate it to a supervisor. If the supervisor can't help, it might go to a specialized technical support team, and so on, until someone in the chain can address the problem. At no point does the customer need to know who will handle their request. They simply submit it to the first point of contact, and it traverses the appropriate path. In software, similar situations arise frequently. You might have a system that processes events, requests, or messages. Different types of events require different processing logic, and sometimes an event might need multiple steps of processing before it's fully handled. If you use a large if-else chain, or a switch statement to decide which handler to invoke, your code becomes monolithic, rigid, and difficult to extend. Adding a new type of request or a new processing step would mean modifying and recompiling this central dispatcher, violating the open-closed principle. The core problem the chain of responsibility pattern addresses is this. How do you decouple the sender of a request from its receiver, allowing multiple objects to have an opportunity to handle the request without the sender needing to know which specific object will handle it? It's about creating a flexible processing pipeline. Why and when to use it, motivation and applicability. The chain of responsibility pattern is useful in situations where more than one object may handle a request, and the actual handler is not known until runtime. The pattern allows you to dynamically define the chain of potential handlers. You want to decouple the sender of a request from its receiver. The sender doesn't need to know the specific object that will handle the request, nor the sequence of potential handlers. It simply passes the request to the head of the chain. You want to give multiple objects a chance to handle a request without hard-coding their relationships. You can change the order of handlers or add new ones to the chain at any time. A request needs to pass through a series of sequential processing steps. Each handler performs its task and then, if necessary, passes the request to the next handler in the chain. Common applications include event processing. Desktop GUI events often use this pattern, where an event, e.g., a mouse click, might be handled by a specific UI component, or passed up to its parent, then grandparent, etc., until a component processes it. Request filtering validation. A series of validators or filters might process a request, e.g., authentication, logging, data validation, caching, before it reaches the core logic. Loan approval systems. A loan application might go through different levels of approval based on the loan amount, credit score, etc., handled by different managers in a hierarchy. A real-world analogy for the chain of responsibility is a fire alarm and firefighting process in a large building. When a smoke detector, the sender initiator, detects smoke, it doesn't try to figure out which specific fire suppression system to activate. It simply triggers the fire alarm. This alarm system then notifies a chain of potential responders. Sprinkler system. If smoke is heavy enough, the sprinkler's first handler might activate. Building occupants. The alarm, another handler, notifies occupants to evacuate. Building management. The alarm system, yet another handler or a separate part of the chain, notifies building security, who might verify and then. Fire department. The alarm system automatically notifies the fire department, final handler. The smoke detector doesn't know who will ultimately put out the fire. It just triggers the chain. Each part of the chain potentially handles the fire event based on its capabilities. Structure, abstracted description for audio. The chain of responsibility pattern typically involves three main roles. Handler, abstract handler. This is an abstract class or interface that defines the common interface for all handlers in the chain. It declares a method for handling requests, e.g., handle request. Crucially, it also declares a method for setting the next handler in the chain, e.g., set next handler. Concrete handler. These are the actual classes that implement the handler interface. Each concrete handler contains specific logic to process a particular type of request or a part of a request. If a concrete handler can process the request, it does so. If it cannot, or only partially, process the request, it forwards the request to its next handler in the chain. If there is no next handler, the request might go unhandled or an error could be thrown. Client. The client initiates the request. It typically holds a reference to the first concrete handler in the chain. It simply sends the request to the head of the chain without knowing which specific handler will eventually process it. Participants, roles defined. Handler defines an interface for handling requests. Optionally, implements the successor link. Concrete handler implements the actual handling logic. If it can handle the request, it does so. Otherwise, it forwards the request to its successor. Client initiates the request to the first concrete handler in the chain. Collaborations, how they interact. The client creates a chain of concrete handler objects, linking them together, e.g., handler 1, set next handler, handler 2. Handler 2, set next handler, handler 3. The client initiates a request by sending it to the first concrete handler in the chain, e.g., handler 1, handle request, some request. Each concrete handler in the chain receives the request. It first determines if it can handle the request itself. If it can handle the request, it processes it, and the chain is typically terminated, though variations exist where the request might still pass through the rest of the chain for logging or other purposes. If it cannot handle the request, it delegates the request to its next handler in the chain. This continues until a handler processes the request or the end of the chain is reached. Consequences, pros and cons. Advantages: reduced coupling. Decouples the sender of a request from its receiver. The sender doesn't need to know who will handle the request, reducing the number of explicit receivers. Increased flexibility. The order and composition of handlers can be changed dynamically at runtime by restructuring the chain. New handlers can be added or removed without affecting existing client code or other handlers. This adheres to the open-closed principle. Simplified client code. The client only needs to know the first handler in the chain, simplifying the calling code significantly. Extensibility. Easy to add new types of requests or new handlers to the chain without modifying existing code. Disadvantages: trade-offs. Guaranteed handling. There's no guarantee that a request will be handled. If no handler in the chain can process the request, it might simply fall off the end of the chain and go unhandled, potentially leading to errors. This needs to be managed carefully, e.g., by ensuring a default handler at the end. Debugging difficulty. Tracing the flow of a request through a long or dynamically constructed chain can be more challenging during debugging. Potential for performance overhead. If the chain is very long, or if many handlers perform checks without actually handling the request, there could be a minor performance overhead due to the traversal. Implementation considerations and variations. Default handler. It's good practice to ensure that requests don't simply fall off the end of the chain. This can be achieved by having a default handler at the end of every chain that handles any unhandled requests, e.g., logs them, returns an error to ensure graceful degradation. Return values completion status. Handlers can return a status indicating whether the request was fully handled, partially handled, or not handled at all. This allows for more sophisticated processing flows. Chain construction. The chain can be pre-built at initialization, constructed dynamically based on configuration, or even built incrementally as requests arrive. Single pass versus multi-pass. Most implementations go through the chain once. For some scenarios, a request might be passed through the chain multiple times, or different parts of the request might be handled by different handlers in separate passes. Using lambdas functions. In languages with strong functional programming support, handlers can sometimes be implemented more concisely using lambda expressions or function pointers, simplifying the concrete handler classes. Related patterns. Composite. Sometimes, composite structures can be used as part of a chain of responsibility if a group of handlers needs to act as a single unit or pass requests to other subgroups. For instance, a department composite might itself be a handler in the chain, delegating to its employee leaf handlers. Command. The command pattern, which we'll discuss next, encapsulates a request as an object. A command object can then be passed along a chain of responsibility for processing. Decorator. Both chain of responsibility and decorator involve chaining objects. The key difference is intent. Chain of responsibility iterates through a chain of potential handlers, each checking if it can handle the request until one does. The request is consumed by one or more of the handlers. Decorator wraps an object, adding responsibilities transparently. Each decorator adds functionality and then passes the request to the next wrapper in the chain for continued processing. The request is consumed by all decorators in the chain. The chain of responsibility pattern is a powerful way to build flexible, maintainable, and extensible request processing systems. By divorcing the sender from the receiver, it helps manage complexity and allows for dynamic configuration of processing pipelines. With this understanding of how requests flow through a chain and how a request can be passed along until handled, we'll now examine another pattern focused on packaging actions. The command pattern. Chapter 16. The command pattern, encapsulating actions as objects. Following our exploration of the chain of responsibility, which streamlines request handling by passing requests along a sequence of potential processors, we now delve into another key behavioral pattern, the command pattern. This pattern redefines how actions are performed within a system by encapsulating a request as an object, thereby allowing for parameterization of clients with different requests, queuing of requests, and support for undoable operations. Imagine you're developing a complex graphics editor. Users can perform various actions: draw a line, move a shape, change color, copy, paste, delete, etc. Traditionally, you might have buttons or menu items that directly call specific methods on a drawing canvas object, like canvas drawline or canvas move shape. This approach has several limitations. Tight coupling. The UI elements, buttons, menus are tightly coupled to the specific methods and objects they invoke. If the underlying rendering engine changes, the UI code might need modification. No undo-redo. Implementing undo-redo functionality would be very difficult. You'd need a separate mechanism to store the state before each action and then figure out how to reverse it. No queuing logging. You couldn't easily queue up a series of operations to be executed later or log all operations for auditing purposes. The core problem the command pattern addresses is this. How do you encapsulate an action or a request as an object, allowing you to parameterize clients with different requests, queue or log requests, and support undoable operations? It treats actions as first-class objects within your system. Why and when to use it, motivation and applicability. The command pattern is particularly useful in situations where you need to parameterize objects with an action to perform. For example, a UI button might perform different actions based on its context, but the button itself doesn't need to know what that action is, only that it's an executable command. You want to specify, queue, and execute requests at different times. This is useful for asynchronous operations, macro recording, or distributed systems. You need to support undo and redo operations. By encapsulating an action, you can store its details and potentially its inverse. You want to centralize the dispatching of requests to relevant objects. You want to log changes for auditing or recovery purposes. Commands can be persistent. Consider a restaurant where orders are taken. A waiter client doesn't shout the complex recipe for spaghetti carbonara directly to the chef receiver. Instead, the waiter fills out an order slip, command object for spaghetti carbonara. This slip contains all the necessary information: what dish, any special requests, the table number, etc. The order slip is then placed on a queue in the kitchen. A chef invoker later picks up the order slip and executes the instructions on it. This system offers great flexibility. The waiter is decoupled from the chef. The waiter doesn't need to know how to cook carbonara. Orders can be queued. If a customer changes their mind, you can potentially undo an order by canceling the slip. New dishes can be added without changing the waiter's ordering process, just by creating new order slips. Structure, abstracted description for audio. The command pattern typically involves 4 main roles. Command, abstract command. This is an interface or an abstract class that declares a method for executing an operation, commonly named execute. For undoable commands, it might also declare an undo method. This is like the generic concept of an order slip. Concrete command. These are specific classes that implement the command interface. Each concrete command holds a reference to a receiver object, the object that will actually perform the action. Calls one or more methods on the receiver to carry out the request. Might store enough state to undo its operation. This is like the spaghetti carbonara order slip, which has instructions for the chef. Client. The client creates a concrete command object and sets its receiver. It decides what action needs to be performed. This is the waiter. Invoker. The invoker holds a command object, or a list of them, and triggers its execution at an appropriate time. The invoker knows how to issue the request by calling execute, but it doesn't know what the request is or who the receiver is. This is the chef picking up the order slip. Receiver. The receiver is the object that performs the actual work required by the request. It has the methods that concrete commands will call. This is the chef who knows how to cook. Participants, roles defined. Command declares an interface for executing an operation. Concrete command implements the command interface. It stores the receiver and optionally the arguments needed for the receiver operation. It defines a binding between a receiver and an action. Client creates a concrete command object and sets its receiver. Invoker asks the command to carry out the request. It holds an instance of the command interface. Receiver knows how to perform the operations associated with the command. Collaborations, how they interact. The client creates a concrete command object, passing it a receiver object, and any necessary parameters for the receiver's operation. The client then hands this concrete command object to an invoker. The invoker stores the command, e.g., in a menu list, a queue, or an undo stack. At some point, the invoker decides it's time to execute the command. It simply calls the execute method on the command object it holds. The concrete command's execute method then calls the appropriate methods on its receiver to perform the actual work. The receiver performs the operation. Consequences, pros and cons. Advantages: decoupling. Decouples the invoker, the object that triggers an operation, from the receiver, the object that performs the operation. The invoker doesn't need to know the specifics of the receiver or the action. Undo-redo functionality makes it straightforward to implement undo and redo mechanisms. Simply store a history of executed command objects and call their undo methods. Queuing and logging. Commands can be queued for asynchronous execution or batch processing, or logged for persistence, auditing, or crash recovery. Macro functionality can easily combine multiple command objects into a composite command to create macros or sequences of operations. Parameterization allows objects like buttons or menus to be parameterized with different actions at runtime. Extensibility, open-closed principle. New command types can be added without changing existing invoker or client code. Disadvantages, trade-offs. Increased number of classes. For every specific action, you typically need to create a new concrete command class. This can lead to a proliferation of small classes, especially for simple systems. Complexity can introduce significant overhead for simple actions that don't need the benefits of undo-redo, queuing, or decoupling. Implementation considerations and variations. Undo-redo stack. For undo-redo, the invoker typically maintains two stacks, an undo stack and a redo stack. When a command is executed, it's pushed onto the undo stack. When undo is called, the top command is popped from the undo stack, its undo method is called, and it's pushed onto the redo stack. Redo works similarly. Macro commands, composite command. A concrete command can itself hold a list of other command objects. Its execute method simply iterates through and calls execute on each subcommand. This allows building complex operations from simpler ones. Smart commands. A concrete command can perform logic beyond simply delegating to a receiver. It can manage state for undo, handle error conditions, or interact with external services. No receiver commands. In some cases, a command might be self-contained and perform its logic without a separate receiver. This might be a command that only logs a message, for example. However, the pattern's true power comes from separating the invoker from a receiver. Lambda functions. In languages that support first-class functions, like Python, JavaScript, or modern C++ and Java with lambdas, simple commands can sometimes be implemented more concisely using functions or lambdas instead of a full concrete command class. However, this often sacrifices explicit undo support unless handled externally. Related patterns. Chain of responsibility. A command object can be passed along a chain of responsibility for processing, where different handlers might choose to execute or modify the command. Memento. The memento pattern, which we'll cover soon, is often used in conjunction with the command pattern to store the state needed to implement undo-redo operations. A command might use a memento to capture the receiver's state before modification and restore it during an undo operation. Composite. As mentioned, composite can be used to create macro commands where a single command can internally execute multiple other commands. Strategy. While both command and strategy encapsulate behavior, their intent differs. Command encapsulates an action or a request that is performed at a specific time, often with a receiver. It's about what to do. Strategy encapsulates an algorithm or a behavior that can be chosen dynamically. It's about how to do something. The command pattern is a versatile and powerful tool for building flexible applications. By transforming actions into objects, it provides incredible capabilities for handling undo-redo, queuing, logging, and decoupling UI from business logic. It's an essential pattern for robust and extensible interactive systems, and it clearly demonstrates the power of treating operations as first-class citizens. Next, we will explore a pattern that helps interpret language and grammar. The interpreter pattern. Chapter 17, The Interpreter Pattern, Understanding Language and Grammar. Following our discussion of the command pattern, which encapsulates actions, we now turn to the interpreter pattern. This behavioral pattern is specialized. It defines a grammatical representation for a language and provides an interpreter to deal with this grammar. It's used when a simple, well-defined language needs to be understood and processed within an application. Imagine you're developing a software application that allows users to filter a list of contacts based on a simple query language. Users might type something like name equals John and city equals New York, or age 30 or profession equals engineer, and country equals USA. This is a small, domain-specific language, DSL. You could parse these strings manually using if-else statements and string manipulations, but as the language grows, this approach quickly becomes brittle, complex, and difficult to extend. What if you want to add support for email like %@example.com or has children equals true? Modifying your parsing logic for every new rule would be burdensome. The core problem the interpreter pattern addresses is this. How do you evaluate sentences in a small, domain-specific language, especially when the grammar for that language is relatively simple and frequent additions or changes to it are expected? It provides a way to represent the grammar rules themselves as objects, making the language processing highly extensible. Why and when to use it, motivation and applicability. The interpreter pattern is most applicable in situations where there is a small, well-defined grammar for an interpretable language. This language could be a query language, a rule engine, or a configuration script. The pattern works best for languages that are not overly complex, e.g., it's not typically used for full programming languages like Java or Python, which require compilers. You need to evaluate expressions in that language frequently. The grammar is likely to change or be extended over time. The pattern makes it easier to add new rules or expressions to the language. Consider a simple regular expression matcher. A regular expression like a BC specifies a language. This expression can be broken down into simpler parts, an OR operation, followed by a literal A, a literal B, and finally a literal C. Each of these parts, or literal, represents a grammatical rule. The interpreter pattern allows you to represent each rule as a class, and then combine these rule objects to form an abstract syntax tree that can then evaluate any given input string. A real-world analogy for the interpreter pattern is a musician reading sheet music. Sheet music has a specific grammar: notes, rests, clefs, time signatures, dynamics, etc. Each symbol represents a terminal expression or non-terminal expression in the musical language. A musician, the client, interprets this sheet music, the abstract syntax tree, and executes the instructions, plays the music. If there are new musical notations, new rules, the musician can learn them and incorporate them into their interpretation without changing their fundamental ability to read music. Structure, abstracted description for audio. The interpreter pattern relies heavily on defining classes for each rule in the grammar. This often results in a recursive structure. Abstract expression. This is an interface or an abstract class that declares an abstract interpret operation. This operation takes a context, an object that holds information needed for interpretation, such as the input string and any variables, as an argument. All expressions, both terminal and non-terminal, will implement this interface. Terminal expression. This represents a terminal symbol in the grammar, the simplest elements of the language that don't need further breakdown. For example, a single number, a literal string, or a variable. Each terminal expression implements interpret and performs a basic operation related to its symbol. Non-terminal expression. This represents a rule that combines other expressions, terminal or non-terminal. For example, and, or, plus, equals. Each non-terminal expression typically holds references to other abstract expression, objects its children, and implements interpret by calling interpret on its children and then combining their results. Context. This object contains global information needed by the interpreter. For a query language, it might hold the input string, variables, or the current state of evaluation. Client. the client builds the abstract syntax tree, a representation of the sentence to be interpreted, using instances of terminal expression and non-terminal expression classes. It then initiates the interpretation by calling interpret on the root of the tree with a specific context. Participants, roles defined. Abstract expression declares an abstract interpret operation that all terminal expression and non-terminal expression classes implement. Terminal expression implements an interpret operation for terminal symbols in the grammar. Non-terminal expression implements an interpret operation for non-terminal symbols. It typically holds references to other abstract expression objects, its children. Context contains information global to the interpreter. Client builds the abstract syntax tree out of terminal expression and non-terminal expression objects and then invokes the interpret operation. Collaborations, how they interact. The client first parses the input sentence of the language into an abstract syntax tree. This tree is composed of nodes that are terminal expression or non-terminal expression objects. For example, for name equals John and city equals New York, the root would be and expression, with equals expression name, John, and equals expression city, New York, as its children. The client creates a context object, populating it with any necessary data, e.g., the current contact record to be filtered. The client then initiates the interpretation process by calling the interpret method on the root of the abstract syntax tree, passing the context. The interpret method on the root non-terminal expression recursively calls interpret on its child expressions. This process continues down the tree until terminal expressions are reached, which perform their basic interpretation. Results from the children are combined as they propagate back up the tree, eventually yielding the final interpretation result, e.g., true or false for a filter or a calculated value. Consequences, pros and cons. Advantages: easy to change add grammar rules. Because each grammar rule is represented by a class, adding new rules or modifying existing ones often means creating a new class or modifying an existing one without affecting other parts of the grammar. This adheres to the open-closed principle. Flexible grammar representation. The abstract syntax tree is a natural way to represent complex language structures, allowing for recursive definitions. Extensible at runtime. You can dynamically assemble and modify the abstract syntax tree at runtime, allowing for flexible interpretation based on user input or configuration. Easier to implement. For simple grammars, implementing the interpreter pattern can be quicker and simpler than building a full-fledged parser and compiler. Disadvantages trade-offs. Requires simple grammars. The pattern is best suited for relatively simple grammars. For complex languages, like a programming language with many keywords, operators, and complex parsing rules, this pattern can lead to an unmanageably large number of classes and become very difficult to maintain. A dedicated parser generator would be more appropriate. Performance overhead. For very large sentences or frequent interpretation, the recursive traversal of the abstract syntax tree can incur performance overhead compared to compiled solutions. Debugging. Debugging issues within a complex recursive interpretation process can be challenging. Implementation considerations and variations. Parsing the input. The interpreter pattern primarily deals with interpreting an already formed abstract syntax tree. The process of parsing the raw input string into this tree is a separate concern. This parsing can be done manually or by using tools like parser generators. Context object design. The context object is crucial. It must contain all necessary information for interpretation, and its design can impact performance, e.g., if it's mutable and needs to be passed around, or if it's large. Alternative for complex grammars. For complex languages, consider using parser generators, like ANTLR, Yak/Bison, or dedicated compiler frameworks, rather than manually implementing the interpreter pattern. Using the visitor pattern, the interpret operation can sometimes become bloated if it needs to handle many different interpretation contexts or generate various representations, e.g., generating code, evaluating, type checking. In such cases, the visitor pattern can be used in conjunction with interpreter to separate the interpretation logic from the grammar classes themselves. Related patterns. Composite. The composite pattern is heavily used in the implementation of the interpreter pattern. The abstract syntax tree is a composite structure, where non-terminal expression objects are composite nodes containing terminal expression leaf and other non-terminal expression, composite, nodes. Visitor. As mentioned, the visitor pattern can be a powerful complement to the interpreter pattern for separating concerns related to interpretation logic. Instead of each expression having an interpret method, a visitor object could perform the interpretation. Strategy. While interpreter defines how to evaluate a language, strategy allows different algorithms, strategies, to be chosen for a particular task. An interpreter might use different strategies for evaluating different types of expressions. The interpreter pattern is a specialized yet elegant solution for defining and evaluating small, domain-specific languages within an application. When applicable, it provides excellent extensibility and a clear mapping between grammar rules and class structures. It reminds us that even abstract concepts like language can be modeled and processed effectively within object-oriented design. Next, we will explore a more common and broadly applicable pattern for navigating collections of objects: the iterator pattern. Chapter 18, the iterator pattern, traversing collections uniformly. After exploring the specialized interpreter pattern for understanding languages, we now turn our attention to one of the most common and fundamental behavioral patterns, the iterator pattern. This pattern provides a way to access the elements of an aggregate object, like a list, an array, a tree, or even a custom collection, sequentially without exposing its underlying representation. Imagine you have a music player application. You might have your music organized in various ways, as a simple flat playlist, a hierarchical folder structure, or perhaps albums sorted by artist. As a user, you just want to press Next Song or Previous Song, regardless of how your music is internally stored. You don't want to know if it's stored in an array, a linked list, or a complex tree structure. You simply want to traverse through the collection. If your client code directly accesses the internal structure of different collections, e.g., looping through an array, using a pointer for a linked list, or recursive traversal for a tree, it becomes tightly coupled to the specific data structure. If you later decide to change how your playlist is stored internally, e.g., from an array to a linked list for faster insertions, all the client code that traverses your playlist would need to be rewritten. This violates the open-closed principle and creates brittle software. The core problem the iterator pattern addresses is this: how do you access the elements of an aggregate object sequentially without exposing its underlying representation, thereby preserving the encapsulation of the aggregate and allowing different traversal algorithms to be used? It abstracts the process of traversing a collection, why and when to use it, motivation and applicability. The iterator pattern is invaluable in situations where you need to access the contents of an aggregate object without exposing its internal representation. This maintains the principle of encapsulation. You need to support multiple traversal algorithms over the same aggregate object. For example, traversing forward, backward, or skipping elements. You need to provide a uniform interface for traversing different types of aggregate objects. Clients can then operate on any collection that provides an iterator, treating them polymorphically. Consider a library. A librarian, the client, doesn't need to know the specific shelving system, array, linked list, tree of every book collection to find a book. Instead, they use a catalog scanner, the iterator. The catalog scanner knows how to navigate its specific catalog, and it always presents the next item in a consistent way. Whether it's a simple list of new arrivals or a complex categorized section, the librarian just asks for the next book. A good real-world analogy for the iterator pattern is a TV remote control for channel surfing. You press the Channel Up button. You don't know or care how the TV internally stores its channels, e.g., as a simple list 2, 4, 5, 7, or a sparse array 101, 105, 203. You simply ask for the next channel, and the remote, the iterator, handles the complexities of finding it and tuning in. The remote acts as an independent traverser of the channel list, abstracting away the TV's internal channel management. Structure, abstracted description for audio. The iterator pattern typically involves four main roles. Iterator, abstract iterator. This is an interface, or an abstract class, that declares the interface for traversing elements. It typically defines methods like hasNext, next, and sometimes first. Concrete iterator. These are the actual classes that implement the iterator interface. Each concrete iterator knows how to traverse a specific concrete aggregate, e.g., a list iterator for an array list, a tree iterator for a binary tree. It maintains the current position within the traversal. Aggregate, abstract aggregate. This is an interface, or an abstract class, that declares a method for creating an iterator object, e.g., create iterator. This method typically returns an object conforming to the iterator interface. Concrete aggregate. These are the actual collection classes, like array list, linked list, binary tree, or your custom playlist. Each concrete aggregate implements the aggregate interface by returning a new instance of its corresponding concrete iterator. For example, an array list would return an array list iterator. Participants, roles defined. Iterator declares the interface for accessing and traversing elements of an aggregate. Concrete iterator implements the iterator interface. It keeps track of the current position in the traversal of a concrete aggregate. Aggregate declares the interface for creating an iterator object. Concrete aggregate implements the aggregate interface and returns an instance of the concrete iterator appropriate for its type. Collaborations, how they interact. The client needs to traverse a concrete aggregate, e.g., a playlist object. The client first requests an iterator from the concrete aggregate by calling its createIterator method, e.g., playlistCreateIterator. The concrete aggregate instantiates and returns a concrete iterator specifically designed to traverse its internal structure. The client then uses this iterator object to traverse the aggregate. It calls hasNext to check if there are more elements and next to retrieve the next element, e.g., while iterator hasNext. Song s equals iterator next. The client remains decoupled from the concrete aggregate's internal representation, interacting only through the generic iterator interface. Consequences, pros and cons. Advantages, encapsulation and decoupling, separates the traversal logic from the underlying collection structure. Clients no longer need to know how the collection is internally organized. This promotes encapsulation and reduces coupling. Multiple traversals. Supports multiple simultaneous traversals over the same aggregate object. Each iterator instance maintains its own traversal state. It also allows for different traversal algorithms, e.g., forward, reverse, skip by n, to be easily implemented for the same collection by providing different concrete iterator implementations. Uniform iteration interface provides a common interface for traversing different aggregate structures. This makes client code more generic and reusable. This is a key benefit, adhering to the open-closed principle. Simplicity and readability simplifies client code by focusing on hasNext and next rather than complex indexing or pointer manipulation. Disadvantages trade-offs, increased complexity, introduces additional classes and interfaces, iterator, concrete iterator, aggregate, concrete aggregate, which can add overhead for very simple collections where the benefits of abstraction aren't significant. External Vs. Internal iterators. The pattern typically describes an external iterator where the client controls the traversal calling hasNext and next. Internal iterators, like for each loops in many languages, handle the iteration internally. While simpler for the client, they are less flexible for complex traversals. The GoF pattern mainly focuses on external iterators. State management. The concrete iterator needs to maintain the state of the traversal, and care must be taken if the underlying collection is modified during iteration, e.g., unsupported operation exception or concurrent modification exception in some languages. Implementation, considerations, and variations. Fluent interface, method chaining. Though less common for iterator itself, the aggregates createIterator method might be part of a fluent interface. Polymorphic iteration. Languages with generics or templates make implementing the iterator pattern very straightforward, allowing iterators to be type-safe for specific collection types. Iterable interfaces. Many modern languages have built-in iterable interfaces, e.g., Python's iterators, Java's iterable and iterator, C's IEnumerable and IEnumerator. These directly embody the iterator pattern, allowing collections to be used in for-each loops. Filtering iterators. An iterator can also filter elements during traversal, presenting only those that meet certain criteria to the client. This is a form of decorator pattern applied to an iterator. Related patterns. Composite. The iterator pattern is often used to traverse composite structures, like file systems or UI component trees. An iterator can be implemented to navigate the hierarchical elements of a composite object. Factory method. The create iterator method in the aggregate interface is a clear example of a factory method. It delegates the creation of the concrete iterator to subclasses of aggregate. Strategy. While iterator defines how to traverse a collection, different concrete iterators can be seen as different strategies for traversal, e.g., depth first, breadth first, reverse traversal. The iterator pattern is fundamental to working effectively with collections in object-oriented programming. It provides a clean, encapsulated, and flexible way to access the elements of various aggregate objects without exposing their internal structure, thereby promoting loose coupling and reusable client code. It's a workhorse of efficient object-oriented design, enabling clear and consistent navigation through data. Next, we will explore a pattern that helps manage complex communication between multiple independent objects. The mediator pattern. Chapter 19, the mediator pattern, orchestrating complex interactions. Transitioning from the iterator pattern, which helps us navigate collections, we now turn to the mediator pattern. This behavioral pattern tackles the often thorny problem of managing complex interactions between objects. It defines an object that encapsulates how a set of objects interact, centralizing communications and preventing objects from explicitly referring to each other. Imagine you're developing a complex graphical user interface, GUI, for an application. You have various UI elements like buttons, text fields, checkboxes, and lists. When a user interacts with one of these elements, it often affects others. For example, clicking a Submit button might validate input fields, disable other buttons, and update a status message. Selecting an item in a list might populate details in adjacent text fields and enable an Edit button. Checking a checkbox might reveal or hide a related section of the form. If each UI element directly communicates with every other element it affects, your code quickly becomes a tangled mess known as spaghetti code. Each element would need to know about and directly reference many other elements, leading to high coupling. Adding a new element or changing an interaction would require modifying numerous existing elements, violating the open-closed principle. This makes the system extremely difficult to maintain, understand, and debug. The core problem the mediator pattern addresses is this: how can you reduce complex interdependencies between a set of interacting objects by centralizing their communication logic in a separate object, thereby improving maintainability and reducing coupling? It's about creating an intermediary that orchestrates communication. Why and when to use it, motivation and applicability. The mediator pattern is particularly useful in situations where a set of objects communicate in complex, well-defined ways, but these interdependencies are difficult to understand or maintain. You want to centralize communication logic. Instead of objects talking directly to each other, they interact through a mediator. You want to reduce strong coupling between objects. By having objects communicate only with the mediator, they no longer need to know about each other's existence, reducing their interdependency. You want to reuse objects, but their interaction logic is not reusable. You can then reuse the objects with different mediators that define different interaction rules. You are designing GUI dialogues or wizards where complex interaction logic exists between many widgets. Consider an air traffic control tower. Each aircraft colleague object communicates only with the control tower, the mediator, never directly with other aircraft. When an aircraft takes off, lands, or changes altitude, it informs the tower. The tower then processes this information, makes decisions, e.g., clearance for landing, instruction to hold, and communicates relevant information to other aircraft if necessary, e.g., aircraft ahead is slowing down. The pilots only need to know how to talk to the tower. They don't need to know the specific communication protocols or positions of every other plane in the sky. Structure, abstracted description for audio. The mediator pattern typically involves two main roles, plus the objects it mediates. Mediator, abstract mediator. This is an interface, or an abstract class, that defines the interface for communicating with colleague objects. It declares methods that colleague objects use to notify the mediator of events or to request actions. Concrete mediator. This implements the mediator interface. It coordinates the interactions between colleague objects, essentially containing the logic for how they all communicate and react to each other. It knows about all the colleague objects it mediates. Colleague, abstract colleague. This is an abstract class or interface for objects that communicate with the mediator. It typically holds a reference to its mediator and has methods to communicate with it. Concrete colleague. These are the specific classes that implement the colleague interface. Instead of communicating directly with each other, concrete colleagues communicate with their mediator when their state changes or they need to interact with other colleagues. Participants, roles defined. Mediator defines the interface for communication between colleague objects. Concrete mediator implements the mediator interface. It knows all its colleagues and coordinates their interaction. It centralizes the communication logic. Colleague defines the interface for objects that interact with the mediator. Each colleague maintains a reference to its mediator. Concrete colleague implements the colleague interface. Each time a concrete colleague performs an action that might affect other colleagues, it notifies its mediator. Collaborations, how they interact. Concrete colleague objects are created, and each is registered with or given a reference to its concrete mediator. The mediator typically holds references to all the colleagues it orchestrates. When a concrete colleague performs some action that needs to involve other colleagues, e.g., a button is clicked, a list item is selected, it notifies its mediator, e.g., mediator button clicked, this, or mediator list item selected, selected item. The concrete mediator receives the notification. Based on its internal logic and the new state or event, it then decides which other concrete colleague objects need to be affected. The mediator then calls methods directly on the relevant concrete colleague, objects to update them or trigger their behavior, e.g., text field set text, item details, edit button enable. Crucially, concrete colleague objects never directly interact with each other. They only know about their mediator. This keeps them decoupled and makes the communication logic explicitly clear within the mediator. Consequences, pros and cons. Advantages, reduced coupling, the primary benefit. It limits strong coupling between objects. Colleagues only know their mediator, not other colleagues. This makes the system more modular and testable. Centralized control and clarity. Centralizes the complex communication logic into a single class, concrete mediator. This makes it easier to understand, maintain, and change the interaction logic. Improved reusability of colleagues. Colleague objects become more reusable because they are no longer dependent on communicating directly with specific other colleagues. They can be plugged into different mediators to achieve different interaction behaviors. Easier to change, add interactions. New interaction rules can often be added by modifying only the concrete mediator, rather than altering multiple colleague classes. Disadvantages, trade-offs. Mediator can become a god object. The concrete mediator can grow very large and become highly complex, accumulating too many responsibilities and becoming a god object or traffic controller. If not designed carefully, this can ironically make the system harder to maintain. Single point of failure, conceptual. If the mediator becomes too complex or experiences issues, it can impact a large portion of the system. Reduced performance, minor. Introducing an extra layer of indirection, communication via the mediator, can introduce a minor performance overhead, though usually negligible. Implementation considerations and variations. Abstract mediator versus concrete mediator. For simpler scenarios, you might implement the mediator interface directly without an abstract mediator if there's only one type of mediator needed. However, The abstract interface is good for flexibility. Colleague-mediator relationship. While a concrete colleague typically holds a reference to its mediator, the mediator often establishes dynamic references to its colleagues, e.g., by registering them. Granular communication. Instead of a single notify, colleague-sender method, the mediator might have more specific methods like notify clicked, button, or notify selected, list. This provides more context to the mediator. Visual editors. The mediator pattern is extremely common in GUI frameworks and visual development environments, where it helps manage the complex interactions between widgets on a form. Separation of concerns within mediator. If the concrete mediator becomes too large, consider breaking down its responsibilities into smaller, more focused helpers or strategies within the mediator itself. Related patterns. Observer. While both mediator and observer, which we'll discuss soon, deal with communication between objects, they do so with different intents and structures. Mediator centralizes complex, known communication among peer objects. The mediator knows about all its colleagues and directly orchestrates their reactions. It's multidirectional and focuses on managing intricate logical flows between specific objects. Observer defines a one-to-many dependency where subjects, publishers, don't know who their observers, subscribers, are. Observers react to changes in the subject's state. It's more indirect and focuses on decoupling notification from reaction. Often, a mediator might use observer internally to allow colleagues to inform the mediator about changes. Facade. Both facade and mediator centralize control over a set of classes. Facade provides a simplified interface to a subsystem of objects, reducing client difficulty. It's about simplifying external client access. Mediator provides a central controller for peer-to-peer communication between a set of interacting objects, reducing their direct dependencies. It's more about internal communication choreography. Singleton. A concrete mediator could potentially be implemented as a singleton if its role is to control a globally unique set of interactions, like a single application-wide event bus. The mediator pattern is a powerful tool for streamlining communication and reducing coupling in systems where many objects interact in complex ways. By isolating interaction logic into a dedicated mediator object, it significantly improves the modularity, maintainability, and extensibility of your software, making tangled webs of communication a thing of the past. Having simplified object interactions, we now look at a pattern that helps us save and restore an object's state, the memento pattern. Chapter 20, the memento pattern, saving and restoring state. Having explored the ways objects interact and orchestrate communication with the mediator pattern, we now turn our attention to another behavioral pattern, the memento pattern. This pattern provides a way to capture and externalize an object's internal state so that the object can be restored to this state later, all without violating encapsulation. Imagine you're using a powerful graphics design application. You've been working on a complex illustration for hours, making numerous changes, adding layers, applying filters, and tweaking colors. At several points, you might want to save a snapshot of your work. Later, if you make a series of changes that turn out to be undesirable, you want to be able to undo those changes and revert to a previous, good state. This is more than just a simple undo-redo of the last action. It's a full restoration of the entire drawing's state at a particular moment. The challenge here is how to capture this complex internal state without exposing all the intricate details of the object's implementation to the outside world. If you expose the internal data directly for saving, you break the object's encapsulation, making it impossible to change its internal representation without also updating all the code that saves and restores its state. The core problem the memento pattern addresses is this: how do you save and restore an object's internal state without exposing the details of that state to the external world, thereby preserving the object's encapsulation? It's about taking a snapshot of an object's current condition for later rollback. Why and when to use it, motivation and applicability. The memento pattern is particularly useful in situations where you need to save, checkpoint, an object's state at a certain point in time so that you can restore it later. This is essential for features like undo-redo, transaction management, or crash recovery. The object's internal state is complex, and/or exposing it directly would violate encapsulation. The memento allows you to capture this internal state as an object without sharing its structure. The object itself needs to be able to save its state, but other objects should not have direct access to its internals. Consider a game where players can save their progress. The game engine, the originator, is a complex object with many internal variables representing the player's position, inventory, score, and the state of the game world. When a player clicks Save Game, the game engine doesn't just pass out all its internal variables to a generic save function. Instead, it creates a save game file object, the memento, which encapsulates all the necessary internal state, often in a serialized format. The game then passes this memento to the file system, the caretaker, for storage. Later, to load game, the caretaker retrieves the memento and passes it back to the originator, which uses it to restore its previous state. The caretaker never needs to peer inside the memento to understand the game's internal state. It just stores and retrieves it. Structure, abstracted description for audio. The memento pattern typically involves three main roles. Originator. This is the class whose state you want to save and restore. It creates a memento containing a snapshot of its current internal state. It also uses a memento to restore its internal state to a previous point. The originator should have access to all the internal state that needs to be stored in the memento. Memento. This is the object that stores the originator's internal state. It usually has two interfaces: narrow interface to caretaker. The caretaker and other external objects can only see a subset of the memento's state, usually just a unique identifier or timestamp. It ensures that the caretaker cannot tamper with the originator's internal state. Wide interface to originator. The originator can access all data stored in the memento to restore its former state. The memento itself is often an opaque object from the caretaker's perspective, meaning the caretaker cannot inspect its contents. Caretaker. This object is responsible for keeping the memento. It requests the memento from the originator and passes the memento back to the originator for restoration. The caretaker performs no operations on or inspections of the memento's contents. It's purely a storage mechanism. Participants, roles defined. Originator, the object whose state is being saved and restored. It creates a memento containing its current internal state and uses a memento to restore its internal state. Memento stores the internal state of the originator object. It should provide a narrow interface to the caretaker to prevent snooping and ensure encapsulation, and a wider interface to the originator for restoration. Caretaker, responsible for the memento's safekeeping. It requests the memento from the originator and passes it back for restoration. It doesn't operate on or examine the contents of the memento. Collaborations, how they interact. At a certain point, the client or an internal process decides that the originator's state should be saved, e.g., a user clicks Save. The caretaker requests a memento from the originator, e.g., memento equals originator create memento. The originator creates a new memento object, copies its internal state into it, and returns it. The caretaker stores this memento object. It holds onto the memento without inspecting its contents, e.g., history add memento. Later, when the originator's state needs to be restored, e.g., user clicks undo or load game, the caretaker retrieves a stored memento and passes it back to the originator, e.g., originator restore memento. The originator then uses the data within the memento to restore its internal state to the point at which the memento was created. Consequences, pros and cons. Advantages, preserves encapsulation, the primary benefit. It allows an object's state to be saved and restored without exposing its internal structure to other objects. This maintains the originator's encapsulation. External simplification. The caretaker is simplified because it doesn't need to know the internal details of the originator's state. It treats the memento as an opaque token. Easy undo redo. Provides a natural mechanism for implementing undo-redo functionality for complex operations or states. Supports transactions. Can be used to implement transaction management, where an object's state can be rolled back to a previous commit point if a transaction fails. Disadvantages, trade-offs. Memory usage. Mementos can consume a significant amount of memory, especially if the originator has a very large internal state or if many mementos are stored, e.g., a long undo history. Complexity can be complex to implement, particularly for originators with many or deeply nested objects, requiring careful deep copying to ensure state independence. Performance overhead. Creating and copying the state into the memento can incur a performance cost. Narrow interface limitation. The caretaker cannot inspect the state of a memento. If a caretaker needs to display a list of save points with descriptions, the memento needs to expose some metadata, e.g., a timestamp or description, through its narrow interface without exposing the full internal state. Implementation, considerations, and variations. Deep copying versus shallow copying. If the originator contains references to other objects, careful consideration is needed. A shallow copy in the memento would mean the originator and memento refer to the same subobjects, leading to unexpected behavior if those subobjects are mutable. A deep copy ensures complete independence but adds complexity. Serialization. In some languages, the built-in serialization mechanisms can be used to implement the memento pattern, as serialization effectively captures and restores an object's state. However, this often gives the caretaker, or anyone with access to the serialized data, the ability to inspect the internal state, potentially breaking encapsulation. The narrow wide interface ensures this cannot happen. Also, serialization couples memento to a specific platform format. History management. The caretaker often manages a stack or list of memento objects for undo-redo. It might also implement strategies for limiting the history size, e.g., discarding oldest mementos. Lightweight mementos. If the state is too large, a lightweight memento might store only the differences, deltas, between states, rather than full snapshots. Restoration then involves applying a sequence of deltas. Related patterns. Command. The command pattern often uses the memento pattern to implement undoable operations. Before a command executes, it asks the receiver, the originator in this context, to create a memento. This memento is stored alongside the command in the undo history. When undo is called on the command, it uses the stored memento to restore the receiver's state. Iterator/composite. If the originator is a complex composite structure, creating a memento might involve traversing and saving the state of all its children, potentially using an iterator. Prototype. The memento pattern can sometimes be implemented using the prototype pattern. The originator can clone itself to create a memento that is an exact copy of its current state. The memento pattern is a clever and elegant solution for state management, particularly valuable for applications that require robust undo-redo capabilities or transactional integrity. It beautifully balances the need for state capture and restoration with the crucial principle of encapsulation, making your objects more resilient and your applications more user-friendly. With our objects now capable of recalling their past, we will next explore how they can keep others informed of their present, the observer pattern. Chapter 21, the observer pattern. Notifying dependence of chain. Continuing our exploration of behavioral patterns, we move from saving and restoring object states with the memento pattern to understanding how objects can communicate changes in their state to others. The observer pattern. This pattern defines a one-to-many dependency between objects so that when one object changes state, all its dependents are notified and updated automatically. Imagine a newspaper or magazine subscription service. When a new edition of a newspaper, the subject or publisher, is published, all its subscribers, the observers, are automatically notified and receive the new content. The newspaper doesn't need to know the specific names or addresses of each individual subscriber. It just knows it has a list of people who are interested in receiving updates. If a new person subscribes, they are added to the list. If someone cancels their subscription, they are removed. The core business of producing the newspaper remains separate from the mechanism of distribution. In software, a similar need arises frequently. You might have a data object, e.g., a stock price, a sensor reading, a game score whose state changes. Multiple UI elements, e.g., a chart, a table, a text display, need to reflect these changes. or perhaps other logic components, e.g., an alerting system, a logging module, need to react to these changes. If the data object directly knew about and called methods on every single UI element or logic component that observes it, it would become tightly coupled to all its dependents. Adding a new dependent would require modifying the data object, violating the open-closed principle. The core problem the observer pattern addresses is this: how do you define a one-to-many dependency between objects, where one object is the publisher and many are subscribers, such that when the publisher object changes state, all its subscribers are notified and updated automatically, without the publisher needing to know anything specific about its subscribers? It's about building a flexible notification system. Why and when to use it, motivation and applicability. The observer pattern is particularly useful in situations where a change to one object requires changing others, but you don't know how many objects need to be changed or which specific ones. An object needs to notify other objects without making assumptions about who those objects are. This promotes tight coupling if unchecked. The set of objects to be changed can evolve dynamically. Dependents can be added or removed at any time. You want to decouple the subject publisher from its observers, subscribers. The subject should not need to know the concrete classes of its observers. Common applications of the observer pattern: GUI event handling. Buttons, text fields, and other widgets often act as subjects that notify observers, event listeners, when user actions occur. Model View Controller, MVC architectures. The model data often acts as a subject that notifies views, UI elements when its state changes. Stock market tickers. A stock price subject notifies various display observers when its value updates. News feeds, RSS. An RSS feed acts as a subject that notifies feed reader observers of new content. Publish-subscribe systems. The observer pattern is the fundamental building block for pub-sub architectures. The real-world analogy of the newspaper subscription service fully encapsulates the pattern's intent. The newspaper subject, publishes, and subscribers, observers, receive notifications. The newspaper doesn't care if a subscriber reads the sports section or the business section. It just delivers the news. Subscribers can choose to subscribe or unsubscribe at any time. Structure, abstracted description for audio. The observer pattern typically involves four main roles. Subject, publisher. This is the object whose state is being observed. It maintains a list of its dependents, observers, provides methods for attaching, subscribe, detaching, unsubscribe, and notifying its observers, notify observers. Observer, subscriber. This is an interface or abstract class that defines an update method. Observers implement this method to receive notifications from the subject. Concrete subject. This is the actual observable object. It stores the state that is of interest to concrete observers. When its state changes, it notifies its registered observers by calling their update method. Concrete observer. These are the specific classes that react to changes in the concrete subject. Each concrete observer implements the observer interface and registers itself with one or more concrete subjects. When notified, it retrieves the necessary state from the subject to perform its update. Participants, roles defined. Subject knows its observers, provides an interface for observers to attach and detach themselves. Observer defines an update interface for objects that should be notified of changes in a subject. Concrete subject stores state of interest to concrete observers, sends a notification to its observers when its state changes. Concrete observer stores a reference to the concrete subject, implements the observer update interface to respond to notifications from the subject. Collaborations, how they interact. Concrete observer objects register themselves with a concrete subject using the subject's attach or subscribe method. Whenever the state of the concrete subject changes, it calls its notify observers method. The notify observers method iterates through its list of registered observers and calls the update method on each one. Each concrete observer receives the update notification. It then queries the concrete subject to get the necessary updated state information and performs its corresponding action, e.g., updates a display, performs a calculation. Consequences, pros and cons. Advantages: Loose coupling. The subject and observer are loosely coupled. The subject knows nothing about the concrete classes of its observers, only that they implement the observer interface. This allows for independent development and modification of subjects and observers. Support for broadcast communication. A subject can broadcast notifications to a large number of observers efficiently. Extensibility. New observer types can be added easily without modifying the subject. This adheres to the open-closed principle. Dynamic relationships. Observers can be attached and detached at runtime, allowing the relationships to change flexibly. Disadvantages, trade-offs, performance overhead. Notification can be slow if there are many observers and frequent updates, leading to a tight loop problem. Debugging difficulty. The indirect nature of communication can make it harder to trace the flow of control and debug issues, especially in complex systems with many subjects and observers. Notification order. The order of notification to observers is not guaranteed unless explicitly managed, which can be an issue if observers have dependencies on each other's updates. Memory leaks, dangling observers. If observers are not detached, unsubscribe, when they are no longer needed, the subject might hold onto references to them indefinitely, preventing them from being garbage collected and leading to memory leaks. This needs careful management. No strong typing for events. In the traditional observer pattern, the update method might be generic. This can mean observers have to cast objects or check types manually, which can be error-prone. Modern event systems often address this with specialized event objects. Implementation considerations and variations. Push versus pull model. Push model. The subject sends detailed information about the change to the observer via the update method's arguments, e.g., update, new stock value. Simpler, but observer might receive more data than it needs. Pull model. The subject only sends a minimal notification, e.g., update, and the observer then pulls the necessary data from the subject by querying it, e.g., observer update, then observer get subject, get state. More flexible, but can involve more calls and couples observer slightly more to subject type. Generally preferred. Generic observer and subject. Most implementations use generic types to make the subject and observer interfaces work with any type of data. For example, observability and observability event payload objects. Instead of passing raw data or having the observer pull data, an event object, or payload, is often passed to the update method, encapsulating relevant information about the change. This provides more context for the observer. Concurrency. In multi-threaded environments, careful synchronization is needed to ensure thread safety when observers are attached, detached, or when notify observers is called. Reactive programming. Modern programming paradigms like reactive programming, e.g., Rx Java, Rx.js, are built directly on extensions of the observer pattern, providing powerful tools for handling streams of events. Related patterns. Mediator. As discussed in the previous chapter, mediator centralizes communication among colleagues. An observer pattern can be used within a mediator to allow colleagues to notify the mediator about changes, with the mediator acting as an observer to multiple subjects. Singleton. A subject or an event bus that manages observer registrations might be implemented as a singleton if it serves as a central notification hub. Publish-subscribe, pub-sub. The observer pattern is the fundamental concept behind the pub-sub model. The distinction often lies in whether the subject directly manages observers, observer pattern, or if an intermediary event bus, or broker, handles the publishing and subscribing, pub-sub. Strategy. An observer's update method might internally use a strategy to decide how to react to a notification. The observer pattern is remarkably powerful for building loosely coupled, event-driven systems. Its simplicity, combined with its flexibility, makes it one of the most widely used and influential patterns in software design, forming the backbone of many dynamic and reactive applications. With objects now capable of notifying their dependents, we next explore how an object can alter its behavior based on its internal state, the state pattern. Chapter 22, the state pattern. Behavior based on internal state. Following our exploration of the observer pattern for managing object dependencies, we now encounter another crucial behavioral pattern, the state pattern. This pattern allows an object to alter its behavior when its internal state changes, making it appear as if the object has changed its class. It's a powerful alternative to using numerous conditional statements to manage state-dependent behavior. Imagine you're developing a vending machine. This machine has several operational states: idle, waiting for money; has money, money has been inserted, waiting for selection; sold out, no items available; dispensing, currently dispensing an item. The behavior of the vending machine, how it responds to events like insert money, select product, dispense, refund, changes dramatically depending on its current state. For example, in the idle state, inserting money changes the state to has money. Selecting a product results in please insert money. In the has money state, inserting more money adds to the balance. Selecting a product might lead to dispensing if funds are sufficient or an error. In the sold out state, inserting money prompts a refund. A common approach to handling state-dependent behavior is to embed large if-else or switch statements within the methods of the vending machine class. For example, insert money might contain a switch statement that checks current state and then executes different code paths. This approach quickly becomes brittle and unmanageable. Adding a new state, maintenance, requires modifying every method that has a state-dependent behavior. Code becomes hard to read, understand, and debug due to the intertwined logic. The class becomes less cohesive, violating the single responsibility principle, as it's responsible not only for its primary function, but also for managing complex state transitions. The core problem the state pattern addresses is this: how do you allow an object to change its behavior when its internal state changes, making it appear as if the object has changed its class without resorting to numerous conditional statements? It externalizes state-specific behaviors into separate state objects. Why and when to use it, motivation and applicability. The state pattern is highly beneficial in situations where an object's behavior depends on its state, and it must change its behavior at runtime depending on that state. Operations have large, multi-branched conditional statements, e.g., switch or if-else, if that depend on the object's state. This is a strong indicator that the state pattern can refactor and simplify the code. You want to move state-specific behavior away from the main class and into separate classes, making the system more modular and easier to extend. A real-world analogy for the state pattern is a traffic light system. A traffic light, the context, can be in a red, yellow, or green state. Its behavior, what lights are on, how it responds to a timer or a sensor, depends entirely on its current state. In the red state, red light is on. When timer expires, it changes to green. In the green state, green light is on. When timer expires, it changes to yellow. In the yellow state, yellow light is on. When timer expires, it changes to red. Instead of having a giant switch statement in the traffic light class for handle timer expired, each state, red state, yellow state, green state, handles the timer expiration differently and explicitly performs the transition to the next state by changing the context's, traffic lights, internal state object. Structure, abstracted description for audio. The state pattern typically involves three main roles. Context. This is the class whose behavior varies depending on its state. It contains an instance of a concrete state subclass, which represents the current state. The context delegates all state-dependent requests to this current state object. It also provides methods to set its current state object. State, abstract state. This is an interface or an abstract class that defines the common interface for all concrete state objects. It declares methods for all actions that are relevant to the different states. These methods take the context object as an argument. Concrete state. These are the specific classes that implement the state interface. Each concrete state implements the state-specific behavior for a particular state. A concrete state object typically knows its context object via the past argument and can initiate state transitions by calling a method on the context to set a new concrete state. Participants, roles defined. Context defines the interface of interest to clients. It maintains an instance of a concrete state subclass that defines the current state. It delegates state-specific requests to its current state object. State declares an abstract interface for encapsulating the behavior associated with a particular state of the context. Concrete state. Each subclass implements a behavior associated with one state of the context. It knows the context intimately and can cause state transitions by changing the context's current state object. Collaborations, how they interact. The context is initialized with a default concrete state object, e.g., idle state for the vending machine. When a client makes a request to the context, e.g., vending machine.insert money, the context delegates this request to its current state object, e.g., idle state.insert money, vending machine. The concrete state object, e.g., idle state, performs the state-specific behavior. Optionally and critically, the concrete state object can decide to transition the context to a new state. It does this by directly calling a method on the context to change the context's internal state object reference, e.g., vending machine change state, new has money state. All subsequent requests to the context will now be handled by the new concrete state object. Consequences, pros and cons. Advantages: eliminates large conditional statements, replaces lengthy, state-checking if else, or switch statements with polymorphism. This makes the code cleaner, more readable, and easier to understand. Encapsulates state-specific behavior. All behavior for a particular state is encapsulated within its own distinct class. This improves cohesion and simplifies individual state classes. Simplifies state transitions. State transitions become explicit and local. Each concrete state class is responsible for defining its own transitions, often by changing the context state directly. Easily add new states. New states can be added by simply creating a new concrete state class and adjusting existing state transition logic where appropriate, without modifying the context class. This adheres to the open-closed principle. Improved maintainability. Changes to the behavior of one state don't affect the others. Disadvantages, trade-offs. Increased number of classes. For every state, you typically create a new class. This can lead to a proliferation of classes, especially for systems with many states and simple behaviors. Complexity for simple cases. For simple use cases with few states and straightforward transitions, the overhead of the pattern might outweigh its benefits, and conditional logic could be simpler. Potential for circular dependencies. Concrete state classes need a reference to the context to change its state, potentially creating bidirectional dependencies. Implementation considerations and variations. Who handles state transition? State objects handle. Each concrete state decides the next state and changes the context state directly. This makes state logic highly cohesive, but couples concrete states to other concrete state classes. As described above, this is common. Context handles. The context determines the next state. Each concrete state only returns some data, and the context uses conditional logic to decide the next state. This keeps concrete states independent, but reintroduces conditional logic back into the context, though typically simpler. Shared state instances. If concrete state objects are stateless, i.e., their behavior doesn't depend on any changeable instance variables, they can often be shared among multiple context instances, potentially making them singletons, e.g., new red light state. This saves memory. Entry-exit actions. Often, methods are added to the state interface, e.g., enter and exit, that are called by the context when a state is entered or exited, allowing for setup and cleanup logic. Related patterns. Strategy. At first glance, state and strategy seem very similar because both use composition to change behavior and adhere to the open-closed principle. The key difference lies in their intent and who initiates the change. State allows an object to change its behavior when its internal state changes. The state object often changes the context state. There's a tight, often fixed relationship between the context and its state implementations. It's about what an object is. Strategy allows a client to choose an algorithm or behavior for an object at runtime. The client usually decides which strategy to use and passes it to the context. It's about how an object does something. Metaphorically, state is like a person being happy or sad. Internal change influences behavior. Strategy is like a person choosing to run or walk. External decision influences behavior. Singleton. If concrete state objects are stateless and can be shared, they are often implemented as singletons. Factory method. A context might use a factory method to create its initial state object or subsequent state objects. The state pattern is an elegant solution for managing complex, state-dependent behavior. By transforming state-specific if-else cascades into polymorphic method calls, it dramatically improves code clarity, modularity, and extensibility. It's a powerful tool for designing systems where an object's nature and responses evolve dynamically, allowing an object to truly appear to change its class. With the ability to make objects respond fluidly to their internal conditions, we now move on to a pattern that allows us to swap algorithms on the fly, the strategy pattern. Chapter 23, the strategy pattern. Swapping algorithms on the fly. Having explored the state pattern, which allows an object to change its behavior based on its internal state, we now examine a pattern that superficially appears similar but serves a distinct purpose. The strategy pattern. This behavioral pattern defines a family of algorithms, encapsulates each one, and makes them interchangeable. Strategy lets the algorithm vary independently from clients that use it. Imagine you're designing an e-commerce application that calculates shipping costs. Depending on the user's preference, their location, or the size of the order, you might use different algorithms for shipping. Standard shipping, e.g. flat rate. Express shipping, e.g. higher rate based on weight distance. International shipping, e.g., complex calculation with customs duties. Free shipping, e.g., for promotional campaigns. If you were to implement this using traditional conditional logic, you might have a calculate shipping cost method with a large if-else structure or a switch statement, checking the shipping type, and then executing the appropriate calculation. This approach has several drawbacks. Lack of flexibility. Adding a new shipping algorithm, like same-day delivery, requires modifying the existing calculate shipping cost method, risking bugs in existing logic. This violates the open-closed principle. Code duplication. Similar logic might be repeated if parts of the calculation overlap. Testing difficulty. Testing each algorithm requires setting up the context, the order calculation class, with specific shipping type flags, which can be cumbersome. The core problem the strategy pattern addresses is this. How do you define a family of algorithms, encapsulate each one as an object, and make them interchangeable, allowing clients to select a particular algorithm at runtime? It's about designing your system so that behavior's algorithms can be swapped out easily. Why and when to use it, motivation and applicability. The strategy pattern is particularly useful in situations where you have multiple algorithms for a specific task and you want to be able to choose between them at runtime. You want to avoid using large conditional statements, e.g., if-else, or switch, to select among related behaviors. You want to separate the algorithm's implementation from the client that uses it. This decouples the client from the details of the algorithms. You have different variations of an algorithm that might change frequently. You want to allow the client to choose the behavior without knowing the details of all possible behaviors. Consider a character in a computer game that has different attack behaviors: a punch attack, a kick attack, or a sword attack. Instead of the character class having if statements to decide which attack animation and damage calculation to use, it delegates to a combat strategy object. The character can then be given a punch strategy, and later, a sword strategy, simply by assigning a different strategy object. A real-world analogy for the strategy pattern is a GPS navigation system offering different routing options. When you input your destination, the GPS, the context, doesn't choose a route randomly. It allows you to select a strategy: shortest route strategy, fastest route strategy, avoid tolls strategy, scenic route strategy. Each strategy implements the calculate route algorithm differently, but they all conform to the common routing strategy interface. You, the user, the client, select which strategy you want, and the GPS applies it. The core GPS system doesn't need to change if a new routing option is added. Structure, abstracted description for audio. The strategy pattern typically involves three main roles. Context. This is the class that uses a strategy object. It holds a reference to a strategy object or an interface it implements. When a client requests an operation, The context delegates the request to its currently configured strategy object. The context is often configured with a strategy by the client at runtime. Strategy, abstract strategy. This is an interface, or an abstract class, that declares the common interface for all concrete strategy implementations. It defines the methods that the context will use to execute the chosen algorithm. Concrete strategy. These are the actual classes that implement the strategy interface. Each concrete strategy implements a specific algorithm or behavior. For our shipping example, this would be standard shipping strategy, express shipping strategy, free shipping strategy. Participants, roles defined. Context maintains a reference to a strategy object. It provides an interface to clients to set its strategy. It delegates behavior to the strategy object. Strategy declares an interface common to all supported algorithms. The context uses this interface to call the algorithm defined by a concrete strategy. Concrete strategy implements the algorithm defined by the strategy interface. Collaborations, how they interact. The client creates concrete strategy objects and provides one to the context. The context maintains a reference to this concrete strategy. This allows the client to select and configure the context with a specific algorithm. The client makes a request to the context, e.g., order.calculate shipping. The context, instead of implementing the algorithm itself, delegates the request to its currently configured strategy object, e.g., current shipping strategy.calculate cost. This context often passes necessary data to the strategy to perform its calculation. The concrete strategy performs the algorithm and returns the result to the context, which then returns it to the client. Consequences, pros and cons. Advantages. Open-closed principle. New algorithms can be added by simply creating new concrete strategy classes without modifying the existing context or client code. This makes the system easily extensible. Eliminates conditional statements. Removes large, complex conditional logic, if else, or switch from the context class, making the context leaner and more focused on its primary responsibility. Decoupling decouples the client from the implementation details of the algorithms. The client only needs to know about the strategy interface. Runtime flexibility allows algorithms to be swapped at runtime, giving the C client the ability to choose or change behavior dynamically based on context or user input. Improved testability. Each concrete strategy can be tested independently, as it is a self-contained unit encapsulating a specific algorithm. Disadvantages trade-offs. Increased number of classes. For every algorithm, you typically create a new concrete strategy class. This can lead to a proliferation of classes, especially for a system with many simple algorithms. Client must choose strategy. The client, or some other part of the system, must know which concrete strategy to instantiate and provide to the context. This moves the responsibility of algorithm selection from the context to the client. Overhead for simple cases. For very few or simple algorithms where the context class is small and unlikely to change, the pattern might introduce unnecessary overhead. Implementation, considerations, and variations. Context passing its data. The context typically passes any data needed for the algorithm as parameters to the strategy's method. This avoids the need for the strategy to hold a reference back to the context, keeping the strategy more independent. Algorithm-specific data. If algorithms need context-specific data, that data should be passed as method arguments to the strategy's operation, or the strategy could be initialized with that data. Stateless strategies. If concrete strategy objects don't contain any unique, mutable state themselves, they can often be shared among multiple context instances, potentially becoming singletons. This saves memory. Dependency injection. The strategy can be injected into the context using dependency injection frameworks, rather than the client explicitly setting it. Related patterns. State, the most common comparison. Both state and strategy have similar structures, a context delegating to a set of concrete objects that implement an interface. The key difference is their intent and how the strategy or state object is changed. Strategy focuses on providing interchangeable algorithms for a client to choose from. The client typically sets the strategy. It's about how something is done. State focuses on allowing an object's behavior to change based on its internal state. The state change is often initiated by the state object itself, changing the context state. It's about what an object is. Template method. The strategy pattern is often used in conjunction with the template method pattern. A template method defines the skeleton of an algorithm in a base class, and the strategy defines the variations for certain steps. Factory method. A factory method can be used by the client to create the appropriate concrete strategy object based on some input or configuration. Bridge. While bridge separates an abstraction from its implementation in two independent dimensions, strategy is about swapping out implementations of a single algorithm dynamically. The strategy pattern is a fundamental tool for creating flexible and maintainable systems where behavior needs to be easily interchangeable. By encapsulating algorithms and making them polymorphic, it empowers you to design cleaner, more extensible code that gracefully adapts to new requirements and variations in functionality. With our ability to swap algorithms at will, we now turn to a pattern that defines the skeleton of an algorithm, the template method pattern. Chapter 24. The template method pattern. Defining an algorithm skeleton. Having explored patterns that allow us to customize behaviors, like strategy for interchangeable algorithms and state for state-dependent actions, we now examine the template method pattern. This behavioral pattern defines the skeleton of an algorithm in a base class, deferring some steps to subclasses. It lets subclasses redefine certain steps of an algorithm without changing the algorithm's overall structure. Imagine you're designing a framework for building reporting applications. All reports generally follow a similar sequence of steps: gather data, retrieve information from a database, file, or web service. Process data. Perform calculations, aggregations, or transformations on the raw data. Format report. Arrange the process data into a structured output format, e.g., HTML, PDF, CSV, plain text. Generate output. Write the formatted report to a file, send it to a printer, or display it on a screen. While the overall sequence of these steps is consistent across all reports, the specific implementation of each step might vary wildly. One report might gather data from a SQL database, another from a flat file. One might sum sales figures, another might calculate averages. One might output to PDF, another to HTML. Without the template method pattern, you might end up with significant code duplication across different report generators, or a monolithic report generator class with numerous if-else statements, or switch statements to decide which specific substep implementation to execute. This makes adding new report types cumbersome and error-prone, as you'd have to copy-paste and modify large blocks of code. The core problem the template method pattern addresses is this: how do you provide a common, fixed structure for an algorithm in a base class, while allowing subclasses to implement or override specific steps of that algorithm without changing its overall sequence? It enforces a consistent high-level process while enabling varied lower-level implementations. Why and when to use it, motivation and applicability. The template method pattern is particularly useful in situations where you want to implement the invariant, fixed, parts of an algorithm once and let subclasses implement the behavior that can vary. This prevents code duplication. You have multiple classes that perform similar steps, but with some variations. The pattern centralizes the common steps. You want to control the execution flow of an algorithm. The base class defines the order of operations, and subclasses can only implement the specific steps, not change the order. You want to provide a framework where developers can plug in their custom logic for specific steps without needing to understand the entire algorithm. Consider a typical software build process. Whether you're building a desktop application, a web service, or a mobile app, the stages often look similar. Fetch dependencies, compile source, run tests, package artifacts, deploy. The specific commands or tools used in each step vary, e.g., Maven versus NPM for dependencies, Java compiler versus Python interpreter, JUnit versus PyTest, but the concept of these stages remains constant. A build process abstract class could define the build template method, calling abstract methods for each stage that Java build process or Python build process subclasses would then implement. A good real-world analogy for the template method pattern is a recipe in a cookbook for baking a cake. The recipe, the template method, defines the overall sequence. Preheat oven fixed. Prepare batter variable. Pour into pan fixed. Bake fixed. Cool fixed. Decorate variable. The exact ingredients and methods for prepare batter or decorate depend on the type of cake, chocolate, vanilla, carrot, which are the subclasses. The core baking process, the template, remains the same, but the specific steps that hook into it are defined by the specific cake recipe. Structure, abstracted description for audio. The template method pattern typically involves two main roles. Abstract class, abstract template. This class defines the template method itself. The template method is a concrete, non-abstract method that defines the overall algorithm, the sequence of steps. It calls other methods, some of which are concrete, implemented by the base class itself, and some of which are abstract, declared in the base class, but implemented by subclasses. These abstract methods are often referred to as hook operations. Concrete class. This class extends the abstract class and implements the abstract hook operations specific to its needs. It provides the concrete implementation for the variable steps of the algorithm defined in the template method. Participants, roles defined. Abstract class defines the template method, which specifies the overall algorithm. It can contain concrete methods for common steps and abstract methods, hook operations for steps that vary. It may also define non-abstract hook operations, methods with default empty or trivial implementations, allowing subclasses to override them if necessary. Concrete class implements the fundamental abstract operations that are part of the template method. It may also override the non-abstract hook operations. Collaborations, how they interact. The client creates an instance of a concrete class, e.g., new HTML report generator. The client then calls the template method defined in the abstract class, e.g., HTML report generator generate report. The template method then executes its fixed sequence of calls to various methods. Some of these methods are already implemented in the abstract class itself. Other methods called by the template method are the abstract hook operations, which are then implemented by the concrete class. This allows the concrete class to provide its specific behavior for those steps. The control flow, the sequence of steps, is entirely managed by the template method in the abstract class. Subclasses can only fill in the missing pieces. Consequences, pros and cons. Advantages, code reusability. The invariant parts of the algorithm are implemented once in the abstract class, reducing code duplication. Inversion of control, Hollywood principle. The abstract class calls back to the concrete class at specific points. This enforces the don't call us, we'll call you principle, giving the framework, the abstract class, control over the high-level flow. Extensibility. New variations of the algorithm can be introduced by creating new concrete classes that implement the abstract steps, without modifying the abstract class or existing concrete classes. This adheres to the open-closed principle. Enforces consistency. Ensures that all implementations adhere to the same high-level algorithm structure, promoting consistency across variations. Disadvantages, trade-offs. Difficulty in changing algorithm structure. Once the algorithm's overall structure is defined in the template method, changing it can be complex if there are many concrete classes relying on it. Increased coupling, subclassing. Subclasses are tightly coupled to the methods defined in the abstract class's template method. Changes to method signatures in the template method necessitate changes in all subclasses. Can be opaque. It can sometimes be difficult to understand the full flow of an algorithm by just looking at the abstract class, without also inspecting the concrete classes that define the specific steps. Implementation, considerations, and variations. Hook operations, concrete methods with default implementation. Besides abstract operations, abstract class can define hook operations, which are concrete methods with empty or default implementations. Subclasses are not required to override these, but can if they need to. This provides optional customization points. Visibility of hook operations. It's common to make the hook operations protected to prevent direct client access, emphasizing that they are internal parts of the template method. Final template method. The template method itself is often declared final in languages that support it, like Java, to prevent subclasses from accidentally or intentionally overriding the overall algorithm structure. Factory methods within template. The template method might use factory methods to create specific objects needed during its execution, giving subclasses control over which concrete objects are used. Combining with strategy. The template method defines the skeleton, and certain steps within the skeleton could be filled in by strategy objects, offering a blend of inheritance and composition for flexibility. For example, a processing data hook could take a data processing strategy. Related patterns. Factory method. As mentioned, factory method is often called by template method to create specific objects needed during the algorithm. Strategy. While strategy defines an entire interchangeable algorithm, a whole recipe swap, template method defines the skeleton of an algorithm, a cookbook recipe with some customizable steps. You can mix and match parts of template method with strategy. For example, one of the steps in a template method could invoke a strategy object to perform part of the overall algorithm, enabling even greater flexibility for that specific step. Bridge. The template method offers a form of abstraction where variations are implemented by subclasses. Bridge separates abstraction from implementation entirely across two hierarchies. The template method pattern is a classic example of how to leverage inheritance to build robust, extensible frameworks. It enforces a consistent flow while providing designated points for customization, making it an excellent choice for designing generic algorithms that can adapt to specific needs without being modified. With the overall algorithm structure defined, our final behavioral pattern, the visitor, will demonstrate how new operations can be added to an existing object structure without altering those structures. Chapter 25. The visitor pattern, operating on elements of an object structure. Having explored various behavioral patterns that manage communication and the flow of algorithms, we come to the final behavioral pattern in our Gang of Four journey, the visitor pattern. This pattern allows you to define a new operation to be performed on the elements of an object structure without changing the classes on which it operates. Imagine you're designing a complex document editor. Your document is composed of various elements: text segments, images, tables, drawings, and groups of these elements, a common composite pattern structure. Now, you need to implement several different operations on this document structure. Export to HTML, traverse the document and convert each element into its HTML representation. Export to PDF, traverse the document and convert each element into its PDF rendering commands. Spell check, iterate through all text-based elements and perform spell checking. Print, send each element to the printer. If you were to add these operations directly to each document elements class, e.g. text segment to HTML, image to PDF, table spell check, it would lead to several problems. Pollution of element interfaces. Each element class would become bloated with numerous operations, violating the single responsibility principle. Scattered logic. The logic for a single operation, e.g. HTML export, would be scattered across many different element classes, making it hard to maintain or change. Difficulty adding new operations. Adding a totally new operation, like grammar check, would require modifying every single element class, violating the open-closed principle. Inability to work with external third-party libraries. If some elements are from a third-party library, you might not be able to modify their source code to add new operations. The core problem the visitor pattern addresses is this: how do you add new operations to an existing object structure, like a tree or graph, without modifying the classes of the elements within that structure, making it easy to add new functionality that varies depending on the type of object it operates on? It separates the capabilities from the objects that possess them. Why and when to use it, motivation and applicability. The visitor pattern is particularly useful in situations where an object structure, like a composite tree or a collection, contains many classes of objects with different interfaces, and you need to perform operations that depend on the concrete classes of these elements. You need to perform many distinct and unrelated operations on objects in an object structure. Putting all these operations into the element classes themselves would bloat their interfaces and make them less cohesive. The object structure is stable and unlikely to change, but you frequently need to add new operations. If the element classes do change frequently, the visitor pattern can become a burden. You need to gather information from multiple element types within the structure to perform a logical operation. Consider a company's organizational chart, a tree structure using the composite pattern. Employees are leaves, departments are composites of employees or other departments. You might need to perform operations like calculate total salaries for a department, summing employee salaries. Generate a performance report, different logic for individual employees versus department summaries. Assign new projects based on roles. Instead of putting calculate salary, generate report, assign project methods on every employee and department class, you can define different visitors: salary calculator visitor, performance report visitor, project assigner visitor. A real-world analogy for the visitor pattern is a tour guide leading different specialized groups through a museum. The museum, the object structure, has many different types of exhibits, element classes: paintings, sculptures, historical artifacts. When a group arrives, e.g., art history students, primary school kids, restoration experts, each group has a different objective and different ways of interacting with the same exhibits. The art history students, group, the visitor, might ask the guide to visit painting and delve deep into its historical context. The primary school kids, group, might visit painting and focus on fun facts and simple colors. The exhibits, the elements themselves, don't change their core nature. Instead, the visiting logic is externalized into the visitor object. Each different group, visitor, implements its own visit methods for each type of exhibit element, specializing the behavior for that specific visit type. Structure, abstracted description for audio. The visitor pattern typically involves 4 main roles. Visitor, abstract visitor. This is an interface, or an abstract class, that declares a visit operation for each concrete element class in the object structure. This means if you have text segment, image, and table elements, the visitor interface will have methods like visit, text segment text, visit, image image, visit table table. Concrete visitor. These are the actual classes that implement the visitor interface. Each concrete visitor implements the specific operations for each type of concrete element. For example, HTML export visitor would implement visit, text segment, to generate p tags, visit, image, to generate im tags, etc. Element, abstract element. This is an interface or an abstract class that defines an accept operation. The accept operation takes an abstract visitor as an argument. All concrete element classes implement this interface. The accept method's job is simply to call the appropriate visit method on the past visitor, passing itself as an argument, e.g., visitor visit this. Concrete element. These are the specific classes that implement the element interface. Each concrete element implements the accept method, which simply calls the appropriate visit method on the visitor it received, passing this itself as the argument. Object structure. This is the collection of element objects, e.g., a list of shapes or a composite tree structure. It's what the visitor will traverse. Participants' roles defined. Visitor declares a visit operation for each concrete element in the object structure. Concrete visitor implements the visitor interface. Each visit method implements a fragment of the algorithm for the corresponding concrete element. Element declares an accept operation that takes a visitor as an argument. Concrete element implements the accept operation. Object structure, a collection or composite of elements that can be visited. Collaborations, how they interact. The client creates an instance of a concrete visitor, e.g., HTML export visitor. The client then initiates the traversal of the object structure, e.g., a list of document elements. For each element in the structure, the client calls the element's accept method, passing the concrete visitor, e.g., element accept HTML exporter. Inside the concrete element's accept method, it calls the corresponding visit method on the concrete visitor, passing itself as an argument, e.g., visitor visit this. This is the key double dispatch mechanism. The specific visit method called depends on both the type of visitor and the type of element. The concrete visitor then executes its specific logic for that type of concrete element. This process continues as the traversal, often managed by the object structure or an iterator, iterates through all elements in the structure. Consequences, pros and cons. Advantages, new operations without altering element classes. The primary benefit. You can add new behaviors to object structures without changing the classes of the elements. This adheres strongly to the open-closed principle concerning new operations. Separation of concerns. Consolidates related operations, like HTML export for all element types, into a single visitor class, rather than scattering them across many element classes. This improves cohesion. Accumulates state. A visitor object can maintain state as it traverses the object structure, allowing it to perform operations that rely on information gathered from different parts of the structure. Breaks cycles in complex graphs. Can simplify operations over complex, potentially cyclical object graphs, though this is a more advanced use. Disadvantages trade-offs. Violates open-closed principle for new element types. If you add a new concrete element type to the object structure, you are forced to add a new visit method to the abstract visitor interface. This then requires modifying every existing concrete visitor class, e.g., HTML export visitor, PDF export visitor, spell check visitor, to implement the new visit method, which can be a significant burden. Increased complexity. Introduces a new layer of interfaces and classes, visitor, concrete visitor element, might be overkill for simple scenarios. Breaks encapsulation. The visitor often needs to access the internal, non-public state of concrete elements to perform its operations. This can sometimes lead to exposing too much of an element's internal details. Visitor coupled to element hierarchy. The visitor interface becomes tightly coupled to the entire element class hierarchy. Implementation considerations and variations. Double dispatch. The accept visitor method on the element and the visit element method on the visitor together implement double dispatch, where the specific operation executed depends on both the type of the visitor and the type of the element. Object structure traversal. The object structure, e.g., composite or other collection, is responsible for iterating through its elements and calling accept on each one. The visitor itself does not typically control the traversal. Default visitor. Provide a default abstract visitor implementation that handles common cases or throws unsupported operation exception for unhandled types. Return values. Visit methods can return values, allowing the visitor to compute and return a result from its traversal. Alternative for small numbers of operations. If you only have a few operations that rarely change and element types change frequently, it might be simpler to add the operations directly to the element interfaces, avoiding the visitor pattern's overhead. Related patterns. Composite. The visitor pattern is very frequently used with the composite pattern. The object structure that the visitor operates on is often a composite of leaf and composite elements. The visitor provides a way to traverse and perform operations on such a tree-like structure. Iterator. An iterator can be used by the object structure to traverse its elements and call the accept method on each one sequentially, triggering the visitor logic. Interpreter. The visitor pattern can be used to implement the interpret operation within the interpreter pattern, especially if a language needs multiple types of interpretations, e.g., parsing, type checking, code generation. The visitor pattern is a powerful and elegant solution for adding new, diverse operations to existing object structures without altering their fundamental design. It's a prime example of turning responsibilities inside out, moving behaviors to separate classes, while it demands careful consideration regarding its trade-offs, particularly with evolving element hierarchies. Its ability to centralize operations and provide immense flexibility for extending functionality makes it a valuable tool in complex object-oriented systems. With the visitor pattern, we conclude our deep dive into the 23 gang of 4 behavioral patterns, having explored how objects interact, manage state, and delegate responsibilities. Next, we will step back and consider how these patterns work together in harmony and the broader implications for software design. Chapter 26, Combining Patterns, Synergy in Software Design. We have journeyed through the 23 foundational gang of 4 design patterns, categorizing them as creational, structural, and behavioral. Each pattern in isolation offers an elegant solution to a specific recurring design problem. However, the true power of design patterns often isn't realized when they are used individually, but when they are combined. Just as instruments in an orchestra play different roles to create a symphony, design patterns can collaborate and complement each other to build more robust, flexible, and scalable software systems. Think of it like building a sophisticated machine. You wouldn't use only screws, or only gears, or only a specific type of lever. You'd use a combination of various fasteners, power transmission components, and mechanisms, each chosen for its specific function, but all working in harmony to achieve the complex overall goal. The same applies to software. Real-world applications rarely benefit from a single magic bullet pattern. Instead, they thrive on the synergistic interplay of multiple patterns. The act of combining patterns allows architects to address different levels and aspects of design complexity. A system might need to create objects flexibly, organize them logically, and manage their interactions dynamically, all at once. This requires a multi-pattern approach. Why combine patterns? Address multiple concerns. No single pattern solves every problem. By combining them, you can tackle diverse challenges simultaneously. For instance, managing object creation, creational, structuring components, structural, and defining their behavior, behavioral. Increased flexibility and extensibility. Patterns often provide specific points of variation, e.g., in a template method, the strategy allows different algorithms for a step. When patterns are combined, these points of variation can be nested, leading to incredibly adaptable designs. You might use one pattern to make your system extensible along one dimension, and another pattern for extensibility along a different dimension. Improved code organization and readability. Strategic pattern combinations can lead to cleaner, more organized code. When a familiar pattern combination is used, developers who understand those patterns can grasp the underlying design intent more quickly. Covering broad architectural needs. Complex systems often require a full architectural approach. Patterns, when woven together, can form cohesive architectural styles, e.g., MVC, layered architectures, microservices that address broad system requirements. Common combinations and their synergies. Many patterns frequently appear together. Here are a few prominent examples we've touched upon. Abstract Factory plus Strategy plus Singleton. Abstract Factory provides an interface for creating families of related products. Strategy allows an algorithm to be chosen at runtime. Singleton ensures only one instance of an object exists. Synergy. An abstract factory might rely on a singleton, e.g., a single widget factory for a specific UI theme. Within that factory, the actual product creation might be handled by strategies that determine how the product is assembled based on configured parameters. This combination enables creating consistent families of objects based on a configuration, abstract factory from a singleton, and allows the logic within those factories to vary dynamically. Strategy. Composite plus iterator plus visitor. Composite represents part-whole hierarchies of objects trees. Iterator provides a way to traverse elements of an aggregate object uniformly. Visitor adds new operations to a structure without changing element classes. Synergy. This is almost a de facto standard combination for tree-like structures. A composite object structure is often traversed by an iterator, e.g., a tree traversal iterator like breadth first or depth first. Once each node, whether a leaf or another composite, is encountered during iteration, a visitor is accepted by that node to perform a specific operation, e.g., print, export, calculate size, based on the node's type. This allows you to define complex tree structures, navigate them without exposing internal details, and add a multitude of new operations without modifying the node classes themselves. Command plus memento. Command encapsulates an action as an object, enabling features like undo redo. Memento captures and externalizes an object's internal state for later restoration. Synergy. This is a classic duo for implementing undo-redo functionality in applications like editors or drawing programs. Before a command executes an action, e.g., moveShape command, it first asks the receiver, the shape to create a memento capturing its current state. The command then stores this memento. When an undo request is made for that command, it uses the stored memento to restore the receiver to its prior state. This cleanly separates the action, command, from the state capture restore memento. Observer mediator, observer, defines a one-to-many dependency for notifications. Mediator centralizes communication between many-to-many interacting objects. Synergy, while distinct, they can complement each other. A mediator can utilize the observer pattern internally to manage its colleagues. Instead of colleagues directly notifying the mediator about every change, they could act as subjects that the mediator observes. This can make the mediator less coupled to specific colleague methods and more reactive to generic events, especially if the colleagues are also subjects to other observers besides the mediator. State plus strategy. State allows an object's behavior to change based on its internal state. Strategy allows an algorithm to be chosen and swapped at runtime. Synergy. These two patterns have very similar structures, leading to frequent confusion. However, they can coexist. A context in a state pattern can delegate certain state-specific actions to a strategy object. For instance, a vending machine context in the has money state might use a discount calculation strategy that changes depending on the total money inserted or customer loyalty. The state defines what happens in that state, and the strategy defines how a specific part of that happens. The ecosystem of patterns. Beyond these direct pairings, patterns contribute to larger architectural patterns or frameworks. Model View Controller, MVC. The observer pattern is fundamental to how the model notifies the view of changes. The controller acts as a mediator between the view and model, interpreting user input and updating the model. Layered architectures. Facades often serve as entry points to different layers, simplifying access. Adapters might be used between layers with incompatible data models or APIs. Dependency injection, DI frameworks. While not a GoF pattern itself, DI is a powerful technique that enables the application of many GoF patterns, e.g., injecting strategies, singletons, abstract factories, by managing the dependencies between objects. Designing with combinations, a mindset. The key to effectively combining patterns isn't to look for places where you can force a pattern. Instead, it's about having a rich vocabulary of solutions. When faced with a complex design problem, decompose it into smaller, manageable subproblems. For each subproblem, identify the most suitable pattern. Then, consider how these individual pattern-based solutions can integrate seamlessly. This often requires a mindset shift from rigid inheritance hierarchies to flexible composition. Many structural patterns, adapter, bridge, decorator, proxy, are powerful examples of using composition to achieve flexibility that inheritance alone cannot provide. Similarly, behavioral patterns like strategy and state rely on composition for their dynamic behavior changes. The decision to combine patterns should always be driven by the specific needs of your system. Where is the coupling too high? Where does flexibility need to be introduced? Where can complexity be effectively managed? Patterns are tools, and selecting the right tool for the job and understanding how tools can be used together is the mark of a skilled craftsman. As you gain experience, you'll start to recognize recurring combinations, almost like architectural idioms. You'll see patterns used to build other patterns, or to provide the necessary infrastructure for another pattern to succeed. This mastery allows you to create software that is not only functional, but also inherently adaptable, maintainable, and robust. With our exploration of how patterns can be combined, we've demonstrated that they are not isolated islands, but interconnected components within the vast landscape of software design. Our next chapter will take a critical look at the flip side. What happens when patterns are misused, or when they are simply not the right fit for the problem at hand, leading to anti-patterns? Chapter 27, Anti-Patterns and When Not to Use a Pattern. We've dedicated many chapters to understanding the power and elegance of design patterns, how they solve recurring problems, and how they combine to create synergistic designs. But just as crucial as knowing when and how to use a pattern is understanding when not to use one, or recognizing the pitfalls of their misuse. This brings us to the concept of anti-patterns. An anti-pattern is the opposite of a design pattern. It's a common response to a recurring problem that is usually ineffective and counterproductive, and which risks being highly destructive. While design patterns are best practices, anti-patterns are worst practices or patterns of failure that lead to negative consequences in software development. Recognizing anti-patterns helps you learn from common mistakes and avoid them. The dangers of misapplying patterns. The Gang of Four patterns are powerful tools, but like any tool, they can be misused. Misapplying a pattern can lead to over-engineering, using a complex pattern where a simpler solution would suffice. This adds unnecessary classes, methods, and layers of indirection, increasing complexity without providing benefits. It's like using a sledgehammer to crack a nut. Increased complexity for no gain. While patterns aim to manage complexity, their misuse can introduce it. A system can become harder to understand, debug, and maintain because the pattern adds indirection where none was needed, making the code obscure. Broken encapsulation or coupling. Some patterns, if implemented carelessly, can inadvertently expose internal details or create tight coupling where none existed, undermining fundamental object-oriented principles. Performance overhead. While typically minor, every layer of abstraction added by a pattern can introduce a small performance cost. When a pattern is used unnecessarily, this cost becomes pure overhead without any accompanying design benefits. Becoming a cargo cult practitioner. This refers to blindly applying patterns without understanding the underlying problem or the pattern's true purpose. It's like building an airplane out of straw and believing it will fly because you've copied the exterior form. True mastery comes from understanding why a pattern works, not just how it's structured. Common anti-patterns related to GoF patterns. While many anti-patterns exist, e.g., God object, big ball of mud, spaghetti code, here are some directly related to the misuse or misunderstanding of the GoF patterns. The singleton addiction / global state overuse. The problem: the singleton pattern is the most frequently misused GoF pattern. Developers often reach for it whenever they need a single instance of something or global access. The anti-pattern: using singleton for every manager or utility class in a system, effectively turning them into disguised global variables. This leads to tightly coupled code, makes unit testing incredibly difficult, and creates hidden dependencies that are hard to track. When not to use singleton. Unless there is an absolute, truly critical reason that only one instance of a class can exist, e.g., a hardware interface that can only have one controller, consider alternatives. Dependency injection. Pass the instance as a constructor parameter or method argument. This makes dependencies explicit and testable. Factory. Use a factory to create and provide the single instance, or limited instances, when needed. Monostate conceptual. All methods are static, but this still leads to global state. Rule of thumb: if it causes difficulties in testing, it's likely an anti-pattern. The factory without a reason / over-abstracting instantiation. The problem: over-enthusiastic application of factory method or abstract factory patterns. The anti-pattern: creating a factory for every single class, even simple ones or those with straightforward instantiation, or when the variety of products is extremely limited and fixed. This adds unnecessary interfaces and concrete factory classes, making the system more complex but gaining no flexibility. It often arises from a misunderstanding that factories are always good. When not to use factories. When object creation is simple, direct instantiation with new is often perfectly fine. Use a factory when the actual type of object to be created varies and isn't known until runtime. The creation process involves complex logic or multiple steps. You need to decouple the client from the concrete product classes. Rule of thumb: don't add a factory if you don't anticipate multiple varying product types or complex creation logic. The strategy everywhere / over-algorithmatization. The problem: applying the strategy pattern to every minor behavior variation. The anti-pattern, creating a strategy interface and multiple concrete strategies for very simple, stable behaviors that are unlikely to change or where a simple if else would be perfectly readable and maintainable. When not to use strategy. When the number of algorithms is small, e.g., 1 or 2, and stable. The behavior is inherently tied to the object and won't change independently. The conditional logic is straightforward and unlikely to create a maintenance burden. Rule of thumb, abstraction adds overhead. Only add it if the flexibility gained outweighs the added complexity. The God object in disguise, e.g., overloaded facade, mediator, or controller. The problem? The facade, mediator, and even UI controllers, often inspired by command or mediator principles, are designed to centralize logic. The anti-pattern, allowing these centralized objects to accumulate too many responsibilities, becoming massive, undifferentiated God objects that know too much and do too much. A facade starts exposing too many subsystem methods, a mediator handles too many disparate interactions, or a controller becomes a single point for all application logic. This violates the single responsibility principle and makes the object very difficult to maintain, test, and understand. When not to overload, constantly evaluate the responsibilities of these centralizing objects. If they grow too large, consider breaking them down into multiple, smaller facades or mediators, each with a more focused scope. Delegating some responsibilities to other helper classes or services. Rule of thumb. If a class's description contains, and multiple times, it does X and Y and Z, it likely has too many responsibilities. The over-abstracted interfaces / excessive interfaces. The problem. A misconception that more interfaces equals better design. The anti-pattern. Creating an interface for every single class, even concrete implementations that serve a very specific, unchanging role. This creates unnecessary files, indirection, and maintenance overhead without providing any polymorphism or extensibility benefits. When not to add an interface, only create an interface when you need to define a contract that multiple concrete classes will implement polymorphism. You want to enable testing by providing a mockable dependency. You want to separate an API from its implementation, API versus SBI. You want to explicitly adhere to the interface segregation principle. Rule of thumb. If a class clearly has only one possible implementation and no immediate need for mocking or abstract contracts, an interface might be redundant. General principles for avoiding anti-patterns. Understand the why. Don't just implement a pattern because it seems cool or because you saw it in an example. Understand the problem it solves and why it's a good solution for that specific problem. Keep it simple, KISS. Start with the simplest possible solution that meets the current requirements. Only introduce a pattern when the complexity it solves, or problems it prevents, justifies the additional complexity it introduces. YAGNI, you ain't gonna need it. Don't prematurely optimize or abstract. Design for immediate needs and known future extensions, not for every conceivable future possibility. Listen to the code. If your code feels forced, convoluted, or hard to test after applying a pattern, it's a strong signal that you might have misapplied it, or that it's not the right pattern for the job. Refactor, don't overdesign. It's often better to start simple and refactor to a pattern once the need truly emerges and the patterns become apparent. This iterative approach helps ensure that patterns are applied contextually and effectively. Test-driven development, TDD. TDD often naturally pushes you towards better design, including the appropriate use of patterns, because it encourages explicit dependencies and testable units, which patterns like strategy and dependency injection facilitate. The journey through design patterns is not just about learning their structures, it's about developing an intuition for good design. This intuition includes recognizing the red flags, the anti-patterns, that signal poor design choices. By understanding both what works and what doesn't, you equip yourself with a truly comprehensive understanding of software architecture, paving the way for elegant, robust, and maintainable systems. Our final chapter will ponder the future of design patterns in an ever-evolving technological landscape. Chapter 28, The Future of Design Patterns, Evolution and New Frontiers. We have journeyed through the timeless domain of the Gang of Four design patterns, dissecting their structure, understanding their purpose, and exploring their nuanced applications. We've learned how to create objects with care, compose them effectively, manage their interactions, and even identify common missteps. As we conclude, it's natural to ponder. What does the future hold for these enduring principles in a rapidly evolving technological landscape? When Design Patterns, Elements of Reusable Object-Oriented Software was published in 1994, it codified proven solutions for object-oriented programming, primarily in C++ and Smalltalk. The software world has transformed dramatically since then. New languages, paradigms, and architectural styles have emerged. Does this render the GoF patterns obsolete? Far from it. Enduring relevance of fundamental principles. The core principles that underpin the GoF patterns: encapsulation, inheritance, polymorphism, composition over inheritance, and the solid principles remain as relevant today as they were decades ago. These are not tied to specific programming languages or frameworks. They are fundamental concepts of good software design. Polymorphism. This cornerstone of object-oriented programming allows patterns like strategy, state, and command to thrive, enabling flexible and interchangeable behaviors. Encapsulation. Patterns like facade, proxy, and memento leverage encapsulation to manage complexity and control access, ensuring modularity. Composition over inheritance. This preference is clearly demonstrated in patterns like decorator, adapter, object adapter, and strategy, which use object composition rather than rigid class hierarchies to achieve flexibility. As long as software involves objects, their interactions, and the need for organized, maintainable code, these patterns will continue to provide a common language and a rich toolkit for designers. The problems they solve are universal: managing complexity, enabling flexibility, improving reusability, and ensuring maintainability. Evolution in practice. While the underlying principles hold, the application and implementation of patterns have evolved. Language features. Modern programming languages often incorporate features that simplify or even directly embody certain patterns. Delegates lambdas first-class functions. Languages with strong functional programming capabilities can often implement simpler versions of patterns like strategy or command more concisely using functions directly rather than requiring dedicated concrete strategy or concrete command classes. Built-in iterators. Most modern languages have built-in iteration constructs, e.g., Python's iterators, Java's iterable/iterator, see #si enumerable I enumerator, that directly implement the iterator pattern. Reflection dynamic proxies. Features like Java's proxy class allow for dynamic creation of proxies and decorators, reducing the need for boilerplate code. Dependency injection, DI frameworks. DI containers, like Spring, Geis, Unity, implicitly manage singletons, ease the injection of strategies and factories, and generally promote loosely coupled code, often implementing aspects of creational patterns behind the scenes. New paradigms and architectural styles. Service-oriented architectures, SOA, and microservices. While the GoF patterns focus on object-level design within a single application, the concepts extend. Services can be facades over complex internal logic, adapters can integrate legacy systems, and load balancers can act as proxies for service instances. Event-driven architectures. These heavily leverage the spirit of the observer pattern, often via dedicated message brokers or event buses that decouple publishers from subscribers at a grander scale. Reactive programming. Frameworks like RX, reactive extensions, are an advanced manifestation of the observer pattern dealing with streams of asynchronous events. Domain-driven design, DDD. DDD emphasizes building software that accurately models a specific business domain. While not directly a pattern, DDD often utilizes patterns like factory to create aggregates, repository to hide infrastructure, and strategy for business rules to build robust domain models. Testability as a design driver. The emphasis on unit testing has highlighted the benefits of patterns that promote loose coupling and explicit dependencies, like strategy, dependency inversion principle, and careful use of singleton. Testability inherently encourages good design patterns, new patterns and pattern languages. The GoF patterns are not the end-all be-all of design. The pattern movement has broadened significantly, leading to enterprise integration patterns, EIP, document patterns for integrating disparate systems, e.g., message bus, content enricher, router. Concurrency patterns address challenges in concurrent and parallel programming, e.g., thread pool, producer-consumer, lock. Architectural patterns describe high-level structures for entire systems, e.g., layered architecture, client-server, peer-to-peer, microkernel. Cloud design patterns emerged to address unique challenges in cloud computing, e.g., retry, circuit breaker, compensating transaction. Game programming patterns specific to game development, e.g., component, state machine, observer with game events. This continuous evolution demonstrates that the pattern concept remains vibrant. New problems arise with technological shifts, and new patterns emerge as developers discover and document effective solutions. The never-ending journey of mastery. Ultimately, the power gained from studying design patterns isn't just about memorizing 23 diagrams. It's about cultivating a deeper understanding of object-oriented design principles and developing the critical thinking necessary to know when and how to apply them. The patterns provide a common language, allowing developers to communicate complex design ideas concisely and effectively. A solution vocabulary, offering proven blueprints for recurring problems, preventing reinvention of the wheel. A foundation for learning, opening doors to understanding more complex architectural styles and new patterns as they emerge. The future of design patterns is not about static adherence to old rules, but about dynamic adaptation. It's about leveraging these enduring principles in the context of new languages, new paradigms, and new problems. The patterns are a stepping stone, a solid foundation from which you can continue to learn, adapt, and innovate. They equip you to not just write code, but to design software craftsmanship. Your journey into mastering the art of software design has just truly begun. Continue to observe, abstract, and communicate, and you will truly unlock the patterns of power.